At work or home, you have a bunch of devices: computers, printers, TVs, and so on. You connect these by means of a network. When the devices are connected, they're able to share data. This could be sending a print job to a printer, sending an email, or streaming video. This can also be used for sharing an internet connection. Mostly, network users are unaware of the network they're using. As long as they can browse the internet, do their job, browse YouTube, they're usually fine. For all of these devices to communicate, they need to be connected together somehow. One way is to plug cables into the devices and connect them to another device called a switch. An example is in a school's computer lab. In this case, a computer in the lab connects to a wall socket with a cable. Another cable runs through the wall, which comes out at a patch panel. This may be in a cabinet on the wall somewhere in the room, or in another room entirely. The port on the patch panel then connects to the switch. You might have a switch at home too. Most homes don't have wall sockets, so devices are connected directly to the switch. We'll talk more about how switches work later. We can also connect devices wirelessly. A common way to do this is to use a wireless access point. A wireless network like this is also called Wi-Fi. An example of this is if you have a tablet. It is impractical to cable it in, so wireless is a good option. The access point is like a switch without cables. More than one device can connect to the access point at a time, but without the messy cabling. The access point can also be connected to the switch with a cable. This way, wired and wireless devices can all be part of the same network. Having both wired switches and wireless access points gives you more connection options. Imagine you have a laptop in an office. You may connect it to the network with a cable when you're at your desk. When you have a meeting in the conference room, you remove the cable and connect to Wi-Fi. Whether wired or wireless, the goal of the network is to move information from one device to another. For this to work, the sender and the receiver must understand each other. They need to speak the same language. In the network, speaking the same language means that devices agree on how data is sent, received, organized, and handled. Basically, they agree on a process that they all follow. It's a bit like filling out paperwork. This is called a protocol. A lot of different protocols are used depending on what's needed at the time. Network software and hardware are designed with these protocols in mind. You will hear of protocols like Ethernet and TCP, which are used for sending and receiving data. You may also hear of protocols like HTTP, which is used for accessing the web, and SNMP, which is used for email. Usually, several protocols are used together to achieve a task. We'll look at protocols further in future videos. In summary, networks are used to connect devices together. Devices use the network to communicate and to share information. To share information, devices need to speak the same language. This language is called a protocol, which is a set of instructions of how to handle the information. Networks connect devices. You could call devices on the network nodes. Nodes may include devices that help control the traffic flowing through a network, like switches and routers. Nodes also include endpoints or hosts. These are devices that send and receive the bulk of the traffic. This includes workstations, servers, printers, and so on. Networks come in different sizes. A network at home is an example of a small network. These networks usually only have a few nodes. This is called a SOHO network. SOHO means Small Office Home Office. These networks typically have a couple of computers, a printer, a few phones and tablets. Some devices will be wireless, and some are connected to a switch. This might be a good time to mention that people often say hub when they mean switch. You can see why, of course, as the switch looks like a central hub in a SOHO network. But please keep in mind that switches and hubs are very different things. Hubs are really old technology that you generally don't see anymore outside of a museum, while switches are modern and commonly used. They look very similar, so it's easy to mix them up. Have a look at the model number to see if it gives you any clues about what the device really is. In a SOHO network, a router is used to connect to the internet. You might find that the router, switch, and access point are all integrated into one device. While a SOHO network will only have a few devices, a corporation, for example a bank, will have many devices. This is called an enterprise network. The enterprise network may cover several floors in a building. They may also have several office buildings in different cities or even across different countries. An internet provider has a very large network. This is called a service provider network. Not only do they provide internet access, they also offer services to connect their customers together. Consider the bank with offices all around the country. The service provider uses part of their network to join these offices together. When devices are collected into a local area, we call this a local area network, or LAN. The LAN may be a small network. In a SOHO network, the LAN is the switch with the handful of devices connected. Or the LAN may be part of a bigger network, like an enterprise network. This network may have many switches, routers, and access points, depending on their needs. Think of the bank from before. They have an office with several floors. You could consider the whole building as a LAN. Or, more likely, the network is broken up into smaller parts. Perhaps there is a separate network on each floor. Each of these could also be called a LAN. These separate LANs may be connected together, but we'll talk more about that later. But a bank's network is going to be larger than just one building. Banks have offices all over the country and all over the world. Even though they are far apart, these networks can be joined together. This is called a WAN, or Wide Area Network. Imagine for a moment that you work for a company with an office in Sydney and an office in Melbourne. You could contact a service provider and they can connect these offices for you. WANs are a topic all of their own, so we'll cover them in detail in a later video. Let's take a moment for a quick summary. All networks are different, and this includes their size. A SOHO network is very small, while an enterprise network may be very large. Of course, your network could fit in anywhere in between. A LAN, or local area network, is a collection of network devices in a local area, like a single building. A WAN, or wide area network, connects networks that are far apart. When it comes to connecting devices, there are two options: wired and wireless. Wired connections have been around since the beginning of time. That's the late 1960s as far as networks are concerned. A wired network uses cables to connect devices together. Wireless technology in general has existed for a long time. Think of radios and mobile phones, for example. The wireless technology that we think of most with networking is called Wi-Fi, which has been around since the early 1990s. Cables can be copper or fiber. Copper cables are usually cheaper and are very common for short distances. Data is sent over copper cables using electrical signals. This means that they can be affected by outside interference. I'll explain why this happens a bit later. Fiber cables are made of strands of glass. Data is sent through the fiber in the form of light. Fiber is more expensive, but it is really good over longer distances. Also, it is not affected by outside interference. A wired LAN uses a protocol called Ethernet. Remember that a protocol is a set of rules that devices in the network agree on. Ethernet is made up of a lot of different parts. Some of these parts describe types of cabling and the speeds that they run at. Other parts describe how the data should be formatted and sent. This is called media access control. The reason Ethernet is layered like this is so devices with different cables and different speeds can all still communicate. Imagine a workstation that has a 1 gigabit connection to the network. It wants to send data to a server that has a 10 gigabit connection. The workstation prepares a message. It formats it according to the media access control rules. Then, it prepares to send the message according to the physical rules that it has to follow. When the server receives the messages, it decodes it at the physical layer. The message that is left is the same as it was at the workstation's MAC layer. As you can see, even though they have different connections, the hosts can still communicate because of this layering system. Ethernet was designed by a group called IEEE. IEEE have created many different standards for different technologies. All of their standards have a code number. Standards that start with 802 are used for LANs. Ethernet, for example, is 802.3. Remember how Ethernet is a group of standards? Each of these is assigned 1 or 2 letters. For example, 10 gig Ethernet is 802.3AN. If you'd like to see a full list of Ethernet standards, have a look at the Wikipedia page on IEEE 802.3. Codes like 802.3AN can be tricky to remember, so each of these physical standards have friendly names, which are a bit easier to understand. For example, 802.3AN is also known as 10G base T. This gives us a bit of a hint about what the standard is. The 10G refers to the speed of the connection. In this case, it is 10 gigabits per second. Base is short for baseband. This means that it uses a digital signal. The alternative is broadband, which uses an analog signal. The T means that this is a UTP cable. I'll explain what a UTP cable is soon. You might see other cables here, like LX, which refers to a type of fiber optic cable. Electrical cables use electrical signals. These are a pattern of 1s and 0s. The receiver needs to decode this pattern. The pattern is called an encoding scheme. To send electrical signals, a circuit is needed. This means that electrical cables need to contain several wires. The most common copper cable is called unshielded twisted pair, or UTP. Modern UTP cables contain 4 pairs of wires, where each pair forms a circuit. Electrical signals over copper cables can be disrupted by interference. Think back to high school science for a while. Do you remember that electricity and magnets are related? Electricity flowing through a copper cable creates a magnetic field. A magnetic field and a copper cable can create electricity. The problem is that a pair of wires running parallel create a small electromagnetic field. The field from one pair of wires can affect the signal on another pair of wires. This is called crosstalk. UTP eliminates most crosstalk by twisting the pairs of wires together. Each pair is no longer running in parallel, so they don't generate the field. If you can, find an old network cable that you don't need. Cut the end off it and strip back the plastic around the outside. You'll probably find 4 pairs of wires, depending on how old the cable is. There may also be a plastic core or a piece of string. They're color-coded, so each pair has a solid color and a striped color. For example, one pair will have brown and striped brown wires. Now I said that you will probably have 4 pairs. There wasn't always 4 pairs though. Older Ethernet standards, such as 10 base T and 100 base T, only needed 2 pairs. But to achieve 1 gig and 10 gig speeds, all 4 pairs are needed. Not only are there different Ethernet standards, but the cable itself has different standards. You will hear of terms like Category 6, or simply Cat6. The category defines things like the number of pairs in the cable, the thickness of the wire, and how tightly they're twisted. For example, Cat2 has only 2 pairs. Cat6 has 4 pairs. Cat6 has thicker wires than Cat5, and so on. Sometimes there'll be an E or an A at the end of the name. Cat5e and Cat6a are examples of this. This is where the original standard has been improved upon. Newer standards support better speeds over longer distances. For example, you can use a Cat5 cable on a 100 meg network. But if you want to run a gigabit network, you need at least Cat5e. If you want 10 gig, Cat6 is okay up to around 55 meters. But if you run Cat6a, you can have a 10 gig link that works up to 100 meters. Each newer standard is backward compatible with the older technology. For example, you can use a Cat7 cable on a 100 meg link. Your cable has a connector at both ends. This is called an RJ45 connector. This is the part that you connect to your network card or switch port. This connector has 8 pins. These line up with the 8 wires inside the cable. The wires need to line up with the correct pins. That's why the wires are color-coded. There are different color schemes you could use. This one here is called 568B. A standard UTP cable will match the wires on both ends. This means that pin 1 connects to pin 1, pin 2 connects to pin 2, and so on. This is called a straight-through cable, as the wires go straight through from one end to the other. Some pairs are used for transmitting data, and others are used for receiving. For example, pair 1 transmits, while pair 2 receives. You'll see here that I've used the terms RX and TX. These simply mean receive and transmit. When you connect a host to a switch, the switch does something very clever. It knows that pair 1 is used for transmitting and pair 2 for receiving. So it does the opposite. It uses pair 1 to receive and pair 2 to transmit. So when the host sends on pair 1, the switch receives on pair 1. The same logic is used on pair 2. The key point here is that a straight-through cable is used to connect a host to a switch. But what if you want to connect a host to something that's not a switch? Perhaps another host or a router? The pins no longer line up correctly. They are both using the same pairs for receive and transmit. So instead, we need to use slightly different cables. What we do use is a crossover cable. This swaps the pairs at one end, so transmit lines up with receive once again. This is also the type of cable you would use if you want to connect one switch to another switch. The alternative to copper cabling is fiber cabling. Fiber cables use strands of glass, which are sometimes called a pipe or a core. A light pulses down the fiber strand, which is received at the other end. Fiber is often used between networking devices, like routers and switches. It may also be used in servers. I've never seen workstations use fiber, but I guess anything's possible. I'm going to take a quick detour and talk about something called duplex. Devices need to both send and receive data. UTP cables can send and receive at the same time. If both ends of the link support this, it's called full duplex. Sometimes a device will not be able to send and receive at the same time. Instead, it will send for a while, stop, and then receive for a while. This is called half duplex. These devices can still send and receive, but they can't do both at once. Full or half duplex is determined by the cabling that's used, the capabilities of the device at both ends of the link, and the software configuration. There are two different ways that fiber can be used. First, you can use single core only. This operates in half duplex mode, as it can't send and receive at the same time. The other option is dual core. This is full duplex, as one core is dedicated to sending and one is dedicated to receiving. Be aware though that it's easy to get the cores mixed up. If you connect the fiber and it doesn't work, try swapping the cores at one of the ends. The enterprise network will mostly use dual core fiber. This means between switches, routers, and servers. Service provider networks, like your internet and WAN providers, often use single core. Now you need to be aware that there are two types of fiber. These are called single mode and multi-mode. They may look the same, but they are different because of the types of light they use. Multi-mode, which is known as MMF, uses a LED light. This is not a particularly powerful light, so it is used over shorter distances, say around 500 meters or less, which makes it useful to connect devices in the same building. The LED light is also cheaper to produce, making multi-mode fiber the cheaper option. Single-mode fiber, or SNMP, uses a laser light. This makes it more expensive, but it is capable of much longer distances. You could easily get 2 kilometers or more, depending on the hardware you're using. You would typically use single-mode fiber between different buildings. Or, your service provider may run single-mode fiber into your building to give you WAN or internet access. Even though a fiber optic cable is made of glass, it is still flexible. You can bend the cable. Well, at least to a point. The fiber cable has a maximum bend radius. The bend radius is how tightly the cable can be coiled up before attenuation occurs. Attenuation is where the signal is degraded or lost. This does not necessarily mean that the cable won't work, but it won't work well. The manufacturer of the cable should be able to tell you what an acceptable bend radius is. There are different connectors that the fiber cables may use. Quite a few, in fact, when you remember that fiber is not just for networking. The main ones we see in data networking are called LC and SC. LC are the smaller connection types, which are usually used on switches and routers. It's common to see these in a dual-core configuration, but they can be separated into single-core. SC connectors are older and larger. They seem to be less common these days. They're more often seen in a wiring closet. Some switches will have a special port that looks empty. Some switches are made up entirely of these ports. These are made for installing a transceiver module. These can be used for different purposes, but basically, they are so you can mix and match the type of cabling you use. Different transceivers support a different cable type. This includes single-mode and multi-mode fiber. Some transceivers will support both, but they also support different speeds, like 1 gig or 10 gig, as well as different cable lengths. For example, a long cable run of 40 kilometers will need a more expensive transceiver than you will need for a 1 kilometer run. The reason that some of these switches have many of these ports is so you can mix and match which transceivers you use for the job. You can even use an RJ45 transceiver for when you want to use UTP copper cable. Wireless, aka Wi-Fi. It doesn't use cabling, of course, but I should mention it quickly anyway. Wireless networks use access points. These devices are like a switch for the wireless network. Wireless devices like your phone or laptop connect to the access point. The access point may also connect to the wired network. This is how wired and wireless devices can be in the same network. Wireless is a good way to connect end-user devices. You wouldn't normally see a server or a router connected to an access point. Wi-Fi does not use the 802.3 Ethernet standard. Instead, Wi-Fi uses the 802.11 standard, which was also created by the IEEE. This describes how radio waves are used to format and encode information and to get different speeds. While they're not the same, Ethernet and 802.11 do share many similarities in the way data is formatted, but that's something we can look at another time. Let's have another quick summary. Networks can be wired or wireless. Wired networks may use copper or fiber cables. In a wired LAN, the Ethernet standard is used to describe how data is formatted. It also covers cable types, link speeds, and how to encode data on the physical link. UTP is the most common copper cable. Modern UTP cable has 4 twisted pairs of wires. Some are used for sending, and others are used for receiving. The cable may be straight through, for connecting devices to a switch, or it may be crossover, for connecting devices to each other. Modern LANs support Auto MDIX, which enable the device to detect the cable used and adapt as needed. A full duplex device can send and receive at the same time. A half-duplex device can only do one at a time. An example of this can be found in fiber cabling. Dual-core fiber is full duplex. Single-core is half-duplex. If you want a short and cheap fiber run, you can use multi-mode fiber. If it has to be longer, you need the more expensive single mode. You also need to use the right transceiver in the device you're connecting the fiber to. If cables aren't going to work for you, then you can consider using wireless access points to create a wireless network. Let's go back to our SOHO network for a while. We use diagrams like this to show how a network fits together. Notice that this is the logical view of the network. It doesn't show all the physical details like the number of switches used, the type of cabling and so on. It's just a simple way to show how things fit together. Imagine that the computer wants to send a print job to the printer. The printer is network enabled, so the computer can send the print job over the network. The network has several endpoints, so how does the computer know where to send the data? Could it just send a message to everything on the network and hope that the right device knows what to do? Well, this does happen on occasion. But if this happened all the time, the network would be very inefficient. Imagine if all the endpoints were sending at once. Also, this could be insecure. What if this was private information? All the other endpoints would see it. And what if there are several printers? Which one would accept the print job? Or do they all start printing? No, the print job needs to be sent only to the correct printer. But how does this happen? Each device on the network has an address. This is like your home address. Your address is unique, and it enables others to find you, contact you, and deliver packages. In a LAN, each device has two addresses. They each have an IP address and a MAC address. These two addresses are used in different ways. We're going to have a brief overview of these addresses here, and dig into more detail in later videos. Let's start with MAC addresses. Each host has at least one MAC address. To be more accurate, each network card has a MAC, so multiple network cards means multiple MACs. When the network card is manufactured, the MAC is permanently assigned. We can't change it. This is also known as the burned-in address. As each network card has its own MAC address, each MAC is guaranteed to be unique. A MAC address is used when one device needs to communicate with another device in the same LAN segment. I'll explain what I mean by this soon. Each device also has an IP address. This address is chosen by us, the network administrators. When we choose addresses, we can make them easier to remember. We also use IP addresses when one device wants to communicate with another, but IP addresses are special, as they allow us to access hosts on a different LAN segment. Imagine that our small company has been very successful and has now grown. Rather than just a single network, we have decided to create a second network. Each of these networks is a LAN segment. These are joined together with a router. This router is part of both LAN segments, so its job is to pass network traffic from one segment to another. MAC addresses are used within the local LAN segment, so when we send a message to, say, a printer in another network, we can't just use the MAC address of the printer. IP addresses, though, are different. We can use the IP address of the printer when we want to send it a message. Let's see how this works. The computer prepares a message for the printer, and it adds the printer's IP address. The printer is on another network, so it needs help to deliver the message. The computer knows that the router can help, so it adds the router's MAC address to the message and sends it. The router receives the message and strips its own MAC address off the message. In its place, it puts the printer's MAC address on instead. The router then forwards the message to the printer. This may raise a lot of questions for you, but don't worry, we'll look at how this works in more detail another time. For now, just remember these things. Hosts have a MAC address and an IP address. A MAC address is used only within a LAN segment. An IP address can be used within a LAN segment, but it is also used to pass traffic to a different LAN segment. All devices on the network have network hardware and software. They need to speak a common language. That is, one host needs to communicate in a way that another host can understand. These languages are called protocols, which we discussed a little in the last two videos. But there isn't just one protocol that makes the magic happen. Several protocols need to work together to get the job done. But trying to track how they all interact can get complicated. And that's why we have network models. They help us to understand how everything fits together. The OSI model can help us to understand the network. It breaks the network up into 7 layers. These layers are physical, data link, network, transport, session, presentation, and application. And if that's a bit tricky to remember, think of this mnemonic. Please do not throw sausage pizza away. I know it's a bit silly, but it helps us to remember the layers and their order. Notice that these are all generic layers. There's no Ethernet layer or email layer. The OSI model is not about specific technologies, but rather how they fit into the network stack. Imagine that we have an application on one host that needs to send data to an application on another host. Let's now see how this data moves through the OSI model. The data, as the application sees it, starts at the application layer. This is where network APIs and apps that access the network live. For example, this includes FTP and web browsing. The data needs to be in a format that can be easily understood. That's what the presentation layer is for. Anything related to data formats lives here, such as image and video files. The session layer tracks application processes. This includes remote procedure calls and service requests. Think of this layer as building a session between a local application and a remote one. You can probably see that the session, presentation, and application layers work with very large pieces of information. But that doesn't work well for lower layers. For instance, what if the data you're transferring is very large? Maybe this doesn't seem like a problem on the surface, but what happens if you get right to the end of the transfer and the connection is interrupted? You would have to start the whole transfer again. Also, any other application that wants to use the network would have to wait until this transfer is complete. Fortunately, there's a way around this. When the data reaches the transport layer, it is broken into manageable chunks. Now, if there's a problem with the data, only one chunk of data needs to be resent, not the entire file. Also, apps can take turns at sending chunks of data, rather than one app hogging the host's resources. This is called multiplexing. Sometimes we need to add more information. Adding the destination address is an example of this. Any information we add to the front of our data is called a header. Any information we add to the back is called a trailer. As you can see, each piece of data gets bigger and bigger as it moves through the network stack. Eventually, the data reaches the physical layer, where it is transmitted over cable or wireless to a remote host. The remote hosts receive the data at the physical layer. The process is then reversed. The data flows back up through the layers. Each layer does its job, removing headers and trailers and converting the data until it is in a form that the application can understand. Can you see here that each layer will only communicate with the layer above and the layer below? Each layer has its own job to do and doesn't get involved with other layers, other than to pass and receive data. You can probably see how this makes it easy to combine different protocols to achieve different tasks. We'll now take a closer look at what each layer does. Afterward, we'll run through an example of how this might work. Developers and application specialists spend a lot of time in the upper layers. This starts with the application layer. This is not strictly the application itself, but rather it's how the application accesses the network. Some examples of this include web browsing, accessing emails, and transferring files. It also includes management sessions like SSH, Telnet, and RDP. The application may contain a lot of data. This data may not always make sense to the rest of the network, so the presentation layer helps by converting it if needed. This conversion may also include services like encryption and compression. File formats also live here, including images and video files. An application may need to talk to several other endpoints, so it is important to track where these conversations are occurring. Each of these conversations is called a session. It's not surprising that this is handled at the session layer. Traffic you would see here includes requests to remote services. You may have heard of Session Control Protocol, or SCP. It lives at this layer too. The transport layer is used to transport traffic between processes onto endpoints. You've probably heard of TCP and UDP. These are the most common protocols used at this layer. Earlier we were talking about how data, if large enough, needs to be taken and broken into manageable blocks. That's part of what this layer does. Generally, we call this block of data a segment. Technically, if you're using TCP, each block is called a segment, but if you're using UDP, each block is called a datagram. So now we have many blocks of data, probably going to different hosts for different applications. So how can we track what goes where? The answer is through port numbers. Each flow of data has a port number associated with the source and destination host. These values are added as part of a header to each block of data. This may be easier through an example. A web server will use port 80 to listen for web traffic. A workstation will send a request to the web server with port 80 in the header. It will also select a source port and send that along as well. The web server will send a response back to the workstation using its port as the destination. But to send information from one host to another, we need some form of addressing. In addition to that, we need a way to route through the network. That's what the network layer is for. One of the common protocols we see here is the Internet Protocol, or IP. This layer adds yet another header. In the case of IP, this includes the source and destination addresses. Once this is done, the block of data is now called a packet. Now we need to think about getting data from one device to another. This is where the data link layer comes in. Notice that the goal is to get data from one device to another. This layer does not try to get data to the end device. That's the responsibility of layers 3 and 4. Part of this includes establishing a logical link between the devices on the same network segment. We need to have a logical link, as devices probably aren't directly connected. They're usually connected with a shared medium, like a switch or over Wi-Fi. A well-known protocol here is Ethernet, which uses MAC addresses. Yet another header is added, which, in the case of Ethernet, includes the source and destination MACs. A trailer may also be added with error correction information. Once the header and trailer are added, this block is now called a frame. As data moves across the network, it will likely pass through one or more routers. As each of these routers are a separate device, the destination layer 2 addresses will change with each hop, but the destination layer 3 address will remain the same. The data link layer is special as it contains two sublayers. The logical link control sublayer is responsible for translating between the network layer and the data link layer. The media access control sublayer is the part that's responsible for adding headers and trailers to the packet, creating the frame. It's also responsible for error correction. And finally, the physical layer. This concerns itself with the physical components of the network. This includes radio frequencies and channels, pulsing light, pins, electrical signals, and standards of copper cabling. Further, this means that the physical layer is responsible for encoding information in a way that can be understood. For example, what electrical signals represent a 1 or a 0? Or what if wireless is used? If you want to dig deeper into this topic, the CCENT guide is quite good. Also, I have more information on my website, and I'll include a link to both of those in the description. How would you like to see an example of how this works? Well, protocols these days do not fit the OSI model exactly. Remember, it's just a reference model to help us. But still, let's try looking at a client sending a request to a web server for a web page. On the client side, the web browser is the application. A user opens a web browser and types in a URL. The web browser uses a protocol called HTTP to prepare the request. This request is the data that needs to be sent to the server. HTTP doesn't simply fit into one layer. If you're sitting an exam, HTTP is considered an application layer protocol. However, practically it spans a few layers. So, we'll say that it's an upper layers protocol. It creates the request that we want to send, and it makes sure any special characters we're sending are properly encoded. HTTP doesn't really manage a session in the upper layers. That's managed by the transport layer. At this layer, a protocol called TCP is used. One of the first things that TCP will do is break the data into segments. We're only talking about a small request here, so TCP shouldn't really need to break up anything in our particular case. It does still need to create the session we were just talking about. The first part of this is assigning port numbers. HTTP usually uses port 80 on the server side. This is the destination port. The client simply generates a random port number and uses this as the source port. These port numbers are added to the data in the form of a header. TCP then stores all this information in memory. This is how it keeps track of the session and knows which application is waiting for the response. Now the network will add addressing information. In our case, we're using IP addressing. It firstly needs to know where to send the request, which it can get from the URL. This becomes the destination address. It also needs the address of the client, so the web server will know who to respond to. This is the source address. These addresses are added to the segment as a header. They are also stored in memory along with port numbers to track the session. But you've probably noticed that the client and server are not directly connected. They're on different networks which are joined by a router. So the packet can't be sent straight to the server. It needs to be sent to the router first. In our data link layer, we have the Ethernet protocol. This creates a logical session with the router. Ethernet will create a header for the packet containing the router's MAC address as the destination and the client's MAC address as the source. Notice that we don't need any MAC addresses for the switch. A simple switch operates at layer 2. It's only there to forward frames to the correct device. Ethernet also includes a small piece of error correction information called a CRC at the end of the packet. And finally, it's time to convert the frame into bits and put them on the wire to be transmitted. Our data moves through the switches without being altered and arrives at the router. The router then takes out the source and destination MAC addresses. It now puts the server's MAC as the destination and its own MAC as the source and sends the packet on. It also generates new error checking information. The server's NIC receives the electrical signals from the cable. At the data link layer, the server will check that there are no errors with the frame by checking the trailer. If all is good, it strips off the layer 2 header and trailer and inspects the IP address information at layer 3. It will check that this packet was indeed meant for itself, and it will store the source and destination IP addresses in memory so it can reply later. It now strips the layer 3 header off and looks at the source and destination ports. It will store these ports in memory along with the IP addresses. In this way, it has also established a session with the client. It sees that the destination port was port 80, and it knows that it has web server software listening on port 80. The data is then given to the correct application, and HTTP will take it from there. Welcome back. In a recent video, we discussed how addresses are important. Devices need them so they know where to send their data. IP addressing is a good example of this. Not only does it include the address of the device, but the address of the network that the device is in. That means, with one simple address, we can find a device on our local network or on the other side of the world. IP addresses come in two different flavors. These are called IPv4 and IPv6, and they look quite different. IPv6 is newer, but IPv4 is still more common, so we're going to focus our attention entirely on IPv4 for now. Firstly, this is what an IP address looks like. It's 4 numbers separated by dots. Each of these numbers is called an octet, as each number is an 8-bit value. We break it up into 4 separate octets to make it easier for us humans. Oh, and if you're having trouble remembering what an octet is, think of an octopus. An octopus has 8 tentacles, an octet has 8 bits. 8 bits means that these numbers can range from 0 to 255. That means that an IP address starts at 0.0.0.0 and ends at 255.255.255.255. We call a range of addresses the IP space. Straight away, you can see that knowing how binary works is important for IP addressing. If you don't know binary, or if you need a refresher, I have a video to help. I'll add it to the description. IP addresses are actually 2 addresses in one. The IP address is the address of the device, but it's also the address of the network that the device is in. 2 addresses in one? How is this possible? Let's take a look at this sample IP address here, 172.16.0.1. The first part, 172.16, refers to the network. The second part, 0.1, is the host address. Don't worry, I'll get to explaining how we know the difference between the two soon. All the hosts here that start with 172.16 are in the same network. If we add more hosts, and the IP addresses start with 172.17, then this is a different network. If hosts in different IP networks need to communicate, then there will need to be a router between them. You're probably wondering, is it always the first half of the address that represents the network? Short answer, no. How then do we know which part of the IP address is the network and which part is the host? The answer to this question, strangely, has changed over time. So let's start back at the beginning and we'll work along from there. When the Internet Protocol was first created, the first octet always represented the network, and the following 3 octets were used for hosts. The largest value that we can get out of a single octet is 255. That means that there was only room for 255 different networks. On the other hand, 3 octets meant that there could be over 16 million host IPs in each network. This sounds a little unbalanced, but in the beginning the internet was not international and there were only a few organizations using it. But as the internet started to grow, it became obvious that this wouldn't work for very long. 255 networks just wasn't enough. So back in 1981, a new method was introduced. This broke the entire IP space into 5 classes. That's class A through to E. Class A, B, and C were used to address devices. Class D is for multicast, and we'll touch on that a little in the next video. Class E is reserved for special purposes. So Class A, B, and C are the ones we need to think about right now. There are a small number of Class A networks, but each network supports a large number of hosts. Class A works a bit like the old method. The first octet is the network, and the remaining 3 octets are for hosts. However, the first bit of the network is always 0. That leaves 7 bits for us to allocate to our networks. That means there are 128 Class A networks with more than 16 million possible host IPs per network. The Class A address space then is 0.0.0.0 through to 127.0.0.0. There is a small catch with this though. Networks starting with 0 and 127 are reserved. So the usable Class A space is really 1.0.0.0 to 126.0.0.0. Class B networks are used for a medium number of hosts. The first 2 octets are used for the network, and the second 2 are used for host addresses. The first 2 bits of the network are always 10, which leaves 14 bits, or 16,384 possible networks. Each network can have over 65,000 hosts. The total Class B IP space is from 128.0.0.0 to 191.255.0.0. Class C are small networks, but there are a lot of them. The first 3 octets are just for the network. The first 3 bits are always 110, leaving 21 network bits, or a little over 2 million networks. With only 1 octet left though, we can have only 256 host IPs per Class C network. The address space ranges from 192.0.0.0 to 223.255.255.0. We can show this as an equation. The number of networks is 2 to the power of n. N is the number of network bits. So Class B has 14 network bits. 2 to the power of 14 is 16,384. The same is true for hosts. Class B has 16 bits for hosts. 2 to the power of 16 is about 65,000. Time to look at an example. If device 172.16.0.1 wants to send a packet to 172.16.0.2, it starts by looking at the first few bits of the destination IP address. As the first 2 bits are 10, it knows that this is a Class B address. It can then assume that the first 2 octets are the network and the last 2 are the host. It sees that the destination network is 172.16, which is the same as its own. As they're in the same network, it can send traffic directly to the destination. Now, what if it wants to send a packet to 172.17.0.1? It does the same thing, and it determines that the destination is on the 172.17 network. This is different to its own network, so it can't send traffic directly. It needs to send traffic to a router first. Take the practice session from before a step further. Tell me which part of each address is the host address. As the internet started to grow, we started using up IP addresses faster and faster, and we started running low on IP addresses again. So in 1993, yet another new method was introduced. It is called Classless Interdomain Routing, or CIDR. Previously, we could identify IP address class by looking at the first few bits. Knowing the class, we then knew which parts of the IP were for the network and which parts were for the host. But now we throw all that away and we introduce something new, the subnet mask. The subnet mask is also made up of 4 octets. This lines up with the IP address bit for bit. The bits set to 1 tell us which part of the IP address is the network. The 0 bits are used for hosts. It's important to notice that all the 1s go on the left and all the 0s go on the right. We never mix up the 1s and 0s in a subnet mask. Take a Class A address for an example. We know 8 bits are used in the network, so the subnet mask would look like this. 8 1 bits for the network, the remaining 24 bits set to 0 for hosts. A Class B address follows the same rules. 16 bits for the network, set to 1, and the host bits set to 0. And finally Class C. Well, you get the idea by now. Is this making sense so far? The subnet mask tells us which part of the IP is for the network and which part is for the hosts. But this hasn't really addressed our original problem yet, has it? So far, we've just seen a different way to show Class A, B, and C addresses. So far, we haven't seen anything on how to save IP addresses. The real power of CIDR is the ability to break a large network into small ones. We call this subnetting. Let's say that you have the classful network of 172.16.0.0. This would have the subnet mask of 255.255.0.0. This allows for about 65,000 hosts. That's a lot of hosts. That might be fine if we have one massive office, but what if we have several smaller offices? Do we want to allocate 65,000 IPs to each office? That seems like overkill to me. So instead, What we can do is we can break the Class B network using our subnet mask. We may decide to use 255.255.255.0 instead. Now, our large office network has been broken into 256 different subnets. Why 256? Well, our subnet mask is now using an additional 8 bits for the network. The largest 8-bit value is 256. Now we can allocate 256 host IPs per network, which is far more reasonable when we have a few small offices. If we want to communicate between our subnets, just like before, we will need a router. Let me take a moment to make sure that I'm clear on this. Devices in the same subnet must be in the same IP network. If not, they will not be able to communicate. Likewise, if devices in the same subnet are separated by a router, they will also not be able to communicate. I'd like to challenge you to think this through for yourself. Take the 172.16.00 network with a subnet mask of 255.255.0.0. If we broke that network up by using the subnet mask of 255.255.240.0, how many subnets do we have? How many host IPs per subnet are there? If you're taking notes, you've probably noticed that it's a pain to write down the subnet masks all the time. To make things simple, we have what's known as CIDR notation. Take 172.16.1.0/24 as an example. The /24 is the subnet mask written in CIDR notation. This means that the first 24 bits of the subnet mask are turned on. It's that easy. We will be using CIDR notation more and more from here on, so try to get more comfortable with it. See if you understand by testing yourself with this example. We have two /24 networks. These are joined together by a small /30 network. A device in network A is unable to communicate with a device in network B. Why are they unable to communicate? Classful is an older method of networking, and subnetting is newer. So why are we even talking about classful networking? Hasn't it been replaced? Yes, it has been replaced. But for one, if you're doing an exam, you may still find exam questions that refer to classful addressing. We also have some remnants of classes in everyday networking. Think of when you set an IP address in Windows, for example. If you configure an IP of 10.8.6.2, Windows will automatically give you the subnet 255.0.0.0. It's assuming classful networking. And while we're mostly classless now, a lot of people tend to think of subnetting as starting with a classful network and breaking it up from there, which is not always strictly true. Sometimes we may have a few small networks and we decide to join them together. This is called supernetting. For example, we may have 192.168.0.0/24 and 192.168.1.0/24. If we want, we can join these into a single network, 192.168.0.0/23. At the end of part 1, we talked about classless interdomain routing, or CIDR. That's where we use a subnet mask to break a network into smaller, better-sized subnetworks. This helps us to conserve IP addresses. We can build on this by introducing to you a concept called Variable Length Subnet Mask, or VLSM. This helps us to conserve even more IP addresses. Let's take our 172.16.0.0/16 network as an example again. We previously spoke about breaking it up into 256/24 networks. We did this because we had several smaller offices rather than one large one. Now, we have 256 IPs in each network. But we also have links between our offices. These are also a kind of network. They may be very small though, with only a router at each end. No printers workstations, or anything like that. If these networks are all /24s, we're wasting over 200 IP addresses per link. What we can do instead is choose one of our /24 networks and break it up even further. Maybe we could break it into /30s. A /30 network uses 30 bits for the network and 2 bits for the host. That's 4 IP addresses in each network. This allows for our 2 routers with 2 IPs to spare. I'll talk about why we're keeping 2 spare a little later on. Now, our original network, 172.16.00/16, has been broken into subnets of different sizes. Some are /24s and others are /30. And that's all VLSM is. It's creating subnets of different sizes. All the IP addresses that we have spoken about so far are addresses that are assigned to devices. As you know, these are also called host addresses. Often our devices only want to send traffic to one other device at a time. This is called unicast traffic. You can think of this as being in a room full of people, and you single one of them out, and you have a conversation with only one person and ignore everyone else. But that's just common sense, right? Isn't traffic always between 2 devices? No, not always. Sometimes a device will want to send a message to every other device in the local network. This may happen if it wants a particular resource, but it doesn't know where it is. It may broadcast a message asking, "Who owns this resource?" or "Where can I find this?" As I've just hinted, this is called broadcast traffic. Imagine you're back in that room full of people, and someone gets up to the microphone and makes an announcement. They're sending a message to everyone at once. To broadcast to every device, we have a special IP address. I'm sure you won't be surprised to find that it's called the broadcast IP. So which IP is the broadcast IP? It is the very last IP in the local network. Always. The last IP address is the IP where all host bits are turned on. Taking the 172.16.2.0/24 network as an example, the last IP is 172.16.2.255. So, as this is special, you can never configure a device with a broadcast IP. And while we're talking about addresses that you can't allocate to devices, there's another one, and that's called the network address. The network address is kind of the opposite to the broadcast address. It is when all the host bits are set to 0. So, 172.16.2.0/24 is a network address. Remember just a few minutes ago when we said we can use a /30 network between our offices? I said that we would need 2 addresses to spare. That's because of the network and the broadcast addresses. A skill you will want to develop is working out what these addresses are in any network, as well as how many addresses you can actually use. Let's take an example. You have a device with the IP 172.16.0.10/24. From the /24, we can see that the first 3 octets are the network and the last octet are the host bits. If we set all host bits to 0, we have 172.16.0.0. That's the network address. If all the host bits are set to 1, we have 172.16.0.255. That's the broadcast address. 8 host bits mean there is a maximum of 256 addresses. We subtract our 2 special addresses and find that we have 254 usable IPs on this network. Now that's not too hard to work out on a /24 network, but when VLSM enters the picture, it can get a little more complicated. Imagine that a device has an IP of 10.42.37.12/22. This is a much more complicated example. While you can sit down and work out all the different ones and zeros, there's another method that many people find easier, and it's called the magic number method. We start with our IP address, and we work out the subnet mask. A /22 has 22 ones, so we get to a subnet mask of 255.255.252.0. Now find the octet in the subnet mask that we need to work with. It's going to be the one that's got a mixture of ones and zeros, so the third octet in our case. Subtract this value from 256. For us, 256 minus 252 is 4. Now we need to know the value of the third octet in our IP. That's 37 in our case. We count by 4 until we find the numbers that are next to the value of the third octet in our IP. That means we want the numbers immediately smaller and larger than 37. If we count by 4, that's 36 and 40. 36 is the start of the network. That gives us the network address. 40 is the start of the next network. So we can go back one IP and that gives us the broadcast. We know there are 10 host bits. That gives us 1024 IP addresses. Subtract our 2 special addresses and we have 1022 usable IPs on this network. Now that is a lot to take in. Go over it a few times and practice. In fact, try a few right now. See if you can work out the network address, the broadcast address, and the number of usable IPs for these networks here. We know that the router helps to get traffic from one network to another. We also discussed how a device knows when to ask the router for help. But how do devices find the router? How do they know where to send their traffic when they need help? When we configure an IP address on, say, a Windows machine, we will also configure a default gateway. This is the local router's IP address. So, when a host has no way of sending traffic to its destination on its own, it will forward it to the default gateway. Some devices call the default gateway the gateway of last resort. I kind of like this term because it really shows us what this IP address is for. If a host runs out of options to handle the data itself, as a last resort, it sends it to the local router. Let's go back to broadcast traffic for a moment. I said earlier that the last IP address in the subnet is the broadcast IP. It's not the only one. There's another special IP used for broadcasts. It's 255.255.255.255. It's different in that it doesn't care what the local subnet is. It basically says, I don't care what network you're on, send this traffic everywhere. There are times when this is useful. One case is when a host is starting up and it doesn't have an IP address yet. We'll get into this a bit more later, but one option is to use a special server to give the host an IP address. But the host doesn't know where the server is yet, so it sends out a broadcast to 255.255.255.255 asking for an IP. So while it's useful, there are also some downsides to broadcasting around like this. Routers are made to forward traffic between networks. So what would happen if they received a broadcast? Well, the larger network could get flooded with broadcast messages. Also, if a broadcast message gets forwarded from one router to another router, it may get stuck in a loop. The simple solution to this is routers never forward broadcast messages. All IP broadcast messages stay within the local network. That makes us wonder then, what if we do need to announce something to other parts of our network? An example of this might be a server that's sending a video stream. Several devices in the network want to tune in and watch this video stream. One option is perhaps we could send video traffic to each device individually. That's the unicast traffic we discussed before. Unfortunately, that's inefficient because we would need to duplicate this traffic for every single recipient. Broadcasting is no good for 2 reasons. First, not all devices want to receive the stream. I mean, what would a printer do with a video stream? Second, broadcasts don't get past the router. So other subnets would not be able to receive the traffic. The way we make this work is with a technology called multicast. Multicast uses special IP addresses. We mentioned this back in the last video when we spoke about Class D. These addresses range from 224.0.0.0 to 239.255.255.255. We won't get into much detail here, but basically multicast is a way for devices to opt in to receiving certain traffic. The video server sends traffic to a multicast IP, and other hosts look for traffic sent to that IP. Routers also forward multicast, so the traffic can reach the networks it needs to get to. So imagine you're back in that room full of people. If all of you broke out into small groups and you spoke to your small group while ignoring everyone else, then you're multicasting. This is a lot of information to take in, so see if you got it all. We just spoke about 3 different special address types. Can you remember what they are and how they work? IP addresses need to be unique if they are to work properly. It's like your home address. If someone somewhere else in the country has exactly the same address as you, your mail might end up at their place, or their mail may end up at yours. So how do we make sure that the IP addresses in your network are unique? What's to stop someone else in another company using the same addresses that you have? IP addresses are managed by an organization called the Internet Assigned Numbers Authority. They give large blocks of addresses to sub-organizations around the world called regional internet registries. Each RIR has a different name. The one that we use here in Australia is called the Asia Pacific Network Information Center, or APNIC. The RIRs then assign blocks of IP space either directly to you, if you're a large enough customer, or they'll also assign blocks to internet providers. Then ISPs, the internet providers, will give some of their space to the smaller customers. While this process is a necessity, there are some problems we'll face. If you want to create a new network, you may need to get more IP space, and that can really slow you down. Also, we use up IP space very quickly. As we have already seen, we run into problems when we run low on IP addresses. So, to address these issues, in the mid-1990s, a standard called RFC 1918 was released. If you're not familiar with RFCs, they're standards that describe how certain internet technologies work. I'll include a link to one of them if you're interested, but be warned they're very detailed and sometimes quite complex, so don't feel obligated to have a read. Anyway, this particular RFC says that some IP spaces are now reserved for private use. You can use these IPs in any way that you see fit within your local network. All other IPs, these are the ones that are assigned to you or to the ISP, are called public IPs. Remember these IPs, the ones you see on your screen here, you will see them a lot in your daily life. But there's something interesting about these addresses. They are not allowed on the internet. Why? Well, this prevents us from overlapping with any other company that is using the same addresses. It also conserves IP addresses, as we don't need to use so many public IP addresses anymore. But if they're not allowed on the internet, how do you get access to the internet? Even with private addressing, you still use some public addressing. At the very least, your internet provider will give you one public address. Let's say you have a device in your network with the IP 172.16.0.1. When it sends a message to the internet router will alter this message to use a public IP address. This is a process called NAT, or Network Address Translation. It's a topic all of its own, so I won't go into any more detail on this right now. We'll cover that in another video some other time. Let me propose this simple question. Which RFC defines private addresses? Which private address ranges does it define? We'll now take a moment to talk about how devices get addresses. There are 2 main ways, and one less common way. First, you can log into a device and configure an address. This is called a static address, as it doesn't change unless you manually reconfigure it. When you assign an IP address this way, you need to choose the address, and you need to make sure it's unique. If 2 devices end up with the same address, we'll have an IP conflict, which causes us all sorts of problems. You'll commonly use this method for devices like routers and some servers, devices whose addresses should never change. The second method is to set addresses dynamically with a DHCP server. A DHCP server has a pool of IP addresses available to it. When a device starts up, it broadcasts a message around the local network to find the DHCP server. The server then gives it an IP address from its pool. The server makes sure that it doesn't give the same IP address to more than one device. Also, there's no guarantee that the device will get the same IP address each time. That's part of what makes this process dynamic. This is good news for workstations, laptops, phones, and tablets. These are devices that may be mobile, and will need to get a new address whenever they move to a new network. There's also a lot of these devices, so it's an easier method than logging into every single device and configuring them manually. Now the third method, it's a little unusual. It's called automatic private IP addressing. And as far as I can tell, only Windows uses it. The basic idea is, you don't statically set an IP address on this machine. The workstation starts and sends a broadcast message to find a DHCP server. However, it doesn't find one. This is when APIPA, did I get that correct? APIPA, yeah, that's right. Now, that is when APIPA kicks in. It picks a random IP from the 169.254.00/16 space and assigns that to the workstation. This kinda has its uses. Perhaps on a small network, if the DHCP server fails, then devices can still reach each other. They won't know what their default gateway should be, so they won't be able to reach other networks or the internet, but at least they can reach each other. Personally, I would not recommend relying on this method. When we looked at the OSI model, we learned how extra headers are added to the data before it is sent. This adds information needed for delivery. It's like writing an address on an envelope. IP is no exception to this. It adds the header that you see here. Not all the details that you will see will make a lot of sense right now. We'll cover a few of the fields, but we won't get into a lot of detail. For now, the two important parts that you need to know are the source and destination fields. And they're pretty self-explanatory. The version field is also easy. It's either for IPv4 or IPv6. Now, this is where it gets interesting. Sometimes a packet is too large for a particular device. So, the device will break the packet into smaller packets and send each of them individually. This is called fragmentation. So, this field here, the fragment offset, tracks the order of these fragments so they can be reassembled in the right order at the destination. But sometimes we decide we want to prevent fragmentation altogether, and we can do that by using the flags field. Here's another interesting one. Remember earlier I said that broadcasts could go round and round and round in circles if routers didn't stop them? Well, the same could happen to other kinds of traffic. So to deal with this, we have this time to live field. The device sending the packet sets a value in this field. Every time the packet passes through a router, the TTL value is lowered by 1. If it gets all the way to 0, the packet is dropped. This is how we prevent a packet from looping forever if there is some sort of error.
We've previously talked about the OSI model, but did you know that it's not the only model out there? Its competition is the TCP/IP model. In this video, we're going to learn about this model and see its perspective on the network. If you haven't seen the OSI video yet, now is the time to go back and check it out. As we discussed there, a model is a set of layers that describe how network hardware and software work together. The goal behind the OSI model was to allow different protocols and vendors to work together. The idea was to build protocols directly based on this model, but we don't see a lot of them today. The main reason is that the protocols from the competition, the TCP/IP model, gained more popularity. The TCP/IP framework was originally developed by the US Department of Defense. Later, various universities and other parties got involved. This led to rapid development, which is probably why it has been more successful than OSI in a practical sense. Now we have protocols like TCP, UDP, and IP, which align directly to this framework. Another reason this framework has been so successful is that it's willing to use existing protocols, like Ethernet, if they already exist. It doesn't try to invent the wheel. Any protocol that is created as part of the framework is defined in an RFC document. Maybe you haven't come across these yet. RFC means request for comments and is a very technical explanation of how the protocol or concept works. Some of these have been around for decades and are still used today. As these documents are available to everyone, any vendor can create hardware and software using these specifications. They'll all work together. Right now, we're looking at RFC 1122, which is the original description of the TCP/IP model released way back in 1989. Now, let's take a look at the TCP/IP model a little closer. Just like OSI, this model is made up of several layers. You can also see that there are two TCP/IP models, which I've listed here as original and current. The original model had 4 layers and was defined in RFC 1122, which we looked at earlier. The revised model splits the bottom layer into 2 separate layers, which we'll talk about soon. The fantastic thing about the current version of the TCP/IP model is that it lines up well with OSI. You can see that the OSI's session, presentation, and application are all rolled into a single application layer. Personally, I prefer this. I like to think of this entire area as the application rather than trying to break it out like OSI does. I also personally think that we can break these models into 2 main areas. The top half is the application and their processes. In the application layer, we're talking about protocols like HTTP for web browsing, SMTP and IMAP for mail delivery, and FTP for file transfers. These applications create processes which listen on particular ports. That's the job of the transport layer, which uses the TCP and UDP protocols. We'll dig deeper into those very soon too. The bottom half focuses on getting the data from one host to the other. The network layer uses the Internet Protocol, or IP. You should be pretty familiar with this from the last 2 videos. The physical and data link layers move the data from device to device, that is, across switches, access points, routers, and other network equipment. Ethernet is a very common protocol here. And on this, we can see that the new version has broken the original link layer into the data link and physical layers. In the old days, there weren't very many different physical connection options. Now we have Ethernet, Wi-Fi, fiber optic cables, and so many more. While it originally did make a lot of sense to break up the physical connections from the data delivery, now we really have to. And that's why we now have 2 layers here instead of 1. Now into some more detail, starting at the top, the application layer. This layer defines the communications between applications on 2 hosts. This doesn't define how the applications work, of course. Instead, it describes on how the applications use the network. More examples here include SSH, Telnet, and RDP for remote administration. But we're just going to focus on HTTP as an example, because even if you don't know it, you're already familiar with it. We start with the applications. These are the web browser on the client side, and the web server software on the server side. HTTP is the protocol that the applications use to communicate. If the browser wants to get a web page from the server, it will send an HTTP request. Just like OSI, the request passes down through the layers on one side and back up through the layers on the other side. Logically, one layer talks to the corresponding layer at the other side. The server will go through the same process to respond with the requested web page. The transport layer creates and maintains conversations between application processes on hosts. This is where TCP and UDP protocols come in. We haven't discussed these a whole lot yet, but put simply, they use port numbers to track sessions. Let's continue using HTTP as our example. The web server may have a process listening on port 80. When the client prepares its HTTP request, it will add a TCP header. We saw headers previously in the OSI video as well. The TCP header contains, among many other things, port 80 as the destination. It will also choose a port to send the request from. After the header has been added, we call this entire piece of data a segment. When the server responds, port 80 is now the source and the client's port is the destination. The combination of port numbers along with IP addresses enables systems to have more than one session open at a time and to track them. Without this, you couldn't have multiple tabs open in your browser, for example. There's a whole lot more to TCP, and we haven't even mentioned UDP yet, so we'll have a look at them in a bit more detail in the next video. Now, back to IP addresses. We've covered them along with routing and subnetting in detail in the last video. When the transport layer is done, the data is passed to the network layer where it is broken into packets, which are manageable chunks of data. We may end up with a single packet or many packets. It all depends on how much data there is to transfer. The point of this layer is to make sure that data from one host can find its way to another host. And to do that, an IP header containing the source and destination IPs is added to every packet. The path from one host to another may cross many networks. Packets need a router to pass from one network to another. That's why it's called routing. When the packets arrive, the host strips the IP headers off and reassembles the packets into the original data before it's passed back to the transport layer. Other network layer protocols you should be aware of are ICMP and ARP, but IP is enough for us right now, so we'll discuss the other two another time. The data link layer is responsible for delivery of traffic on a single network segment or LAN. In TCP/IP terms, this means delivery within a single subnet. Common protocols here are Ethernet and point-to-point protocol. Ethernet is very common, so we'll use that as our example. An address, called a MAC address, is assigned to every device. Other protocols will use some form of addressing as well. To add these addresses, we add another header. In the case of Ethernet, a trailer is added as well. This entire piece of data is called a frame. If the two hosts are in the same subnet, then delivery is simple. One host just sends to another. But if they are in different subnets, we need a router. That means that the destination MAC will be the MAC of the router itself. When the frame reaches the router works out where it needs to send the packet by looking at the destination IP in the IP header. It then sets its own MAC as the source and the next device as the destination. If there are several routers in the path, the MAC addresses in the frame will be rewritten several times along the way. The physical layer is exactly what the name suggests. It's responsible for physically transmitting and receiving data. There are many ways this can be done. Electrical, radio, and light signals are the options that come to mind. In any case, the data is encoded and the bits are transmitted over the medium. This will likely happen a few times along the path, like copper from workstation to a switch, fiber between switches, and copper through to the destination. You've used TCP many times, and probably not even known it. It's the feature-rich transport protocol, and the one that forms connections. It's time to see how these connections work. After a while, it will eventually be time to close the connection. This could be because a process is complete, say a file transfer has finished. Or perhaps one device has taken too long, and the other is sick of waiting. Or maybe something is wrong with the connection, and it needs to be terminated. There are two ways this can be done, and either client or server can start the process. Firstly, we'll look at the graceful way to close a connection. One of the devices will send a TCP segment with both the FIN and ACK flags sent. FIN is short for finished. The other device replies with an ACK message. It will immediately follow up with a FIN ACK message of its own, which is acknowledged with another ACK message. So there's a lot going on just to close a connection. 4 messages. and they appear to be duplicates. So why are there two pairs of the same sets of messages? The first pair announces and acknowledges the intention to close the connection. The responder now needs to notify the application that the connection is closing. It might take a few seconds for the application to deal with this. The second pair of messages are sent only when the application is ready. Using two pairs of messages will give the application time to respond before the connection is fully closed. Now, the second way to close the connection. This is the non-graceful method. One device will need to close a connection and send a TCP segment with the RST flag. This means connection reset. And that's it. There's no graceful waiting for the application, there's no acknowledgements, the connection is just dropped. This type of closure would only happen if there's an error. It's common to see, for example, if a client tries to connect to a port that's not open. That is, there's no application using the port. So a reset message is sent before the three-way handshake even completes. But that raises another interesting question. Why are there two ways to close a connection? Isn't one enough? Well, reset messages only happen if there's an error, so this happens with troubleshooting. So if we're trying to narrow down a network issue, one thing we could look for is reset messages. We've been on a journey through the transport layer, looking at TCP, UDP, and what makes them the same and what makes them different. It's now time for the last mile of this journey as we look at error recovery and windowing. Data can be lost for so many reasons. These errors are generally detected by the data link protocol, like Ethernet, which will drop bad frames. Both TCP and UDP have some error handling built in. They can detect corruption by using the value in the checksum field. But only TCP is considered reliable. This is because it will manage retransmission of the lost data. UDP, on the other hand, is considered unreliable, as it will not try to recover from data loss. To understand how this works, we must first look at how the segments are acknowledged. You'll remember that when a segment is received, the receiver sends an acknowledgement message confirming that it got the data. In the last video, we saw that there are sequence numbers in the TCP header. One function of this is to reassemble the segments into the correct order, but they also affect acknowledgements. Think of the three-way handshake. Let's say that the sequence number was initialized to 97, and that was sent in the SYN message. The SYN ACK message would use a sequence of 98, and the final ACK would be 99. After the handshake is complete, the meaning of this sequence number changes. It won't count the number of segments sent back and forth anymore. Instead, now it will count the number of bytes that have been sent. The first segment that carries data then would have a sequence number of 100, as it's the next sequence number. Let's now say that this segment is 100 bytes long. The server will get this segment and will need to send back an acknowledgement. It doesn't just send the ACK flag though, it also uses the acknowledgement field. It will set this value to 200. Why? Because it's using a process called forward acknowledgement, where it's acknowledging the data that has been sent and telling the sender what it's expecting to get next. So why 200? We started with a sequence number of 100. We sent 100 bytes, and now we're ready for the data starting at byte number 200. When the next segment is sent, the sequence number is set to 200. Do you see how the sequence numbers track not the number of segments, but the number of bytes being transferred? The advantage to this is if data went missing, there would be no acknowledgement for that range of bytes. The sender could then resend that range of data. But it's not very efficient to send an acknowledgement for every single segment. The sender would need to stop sending and wait for the ACK message before sending the next segment. The receiver would also need to spend more compute power generating these messages. So, to make it more efficient, TCP uses a process called windowing. This allows the sender to send a certain amount of data, usually over multiple segments, and the receiver can send one single acknowledgement to cover all of them. The amount of data that can be acknowledged in a single message is called the window size. This value is stored in the window field of the TCP header. Imagine that the window size is 1000 bytes. In the real world it would be much larger, but we're just using simple numbers for the example. The sender now sends a segment with 100 bytes of data. The window size shrinks by 100 bytes to 900 bytes. There's no need to send an acknowledgement back yet, as there is still room in the window. The sender sends 9 more 100 byte segments. The window shrinks by 100 bytes each time, and when the window reaches 0, the sender will stop and wait until it receives an acknowledgement. Once acknowledged, the window size resets back to 1000 bytes. In the real world, the receiver will not wait for the window to shrink to 0 before sending an acknowledgement. This is so the sender does not have to stop and wait for the acknowledgement, which is better for traffic flow. Now we've covered that, we can look at error recovery. Think of the example once again. Now imagine that there's a problem somewhere, and the 4th segment does not arrive. It's time for error recovery to kick in. The server has received 9 segments, but bytes 400 to 499 are missing. It knows this because the 3rd segment starts at byte 300, it is 100 bytes long, so the next segment should start at 400. But, after waiting a reasonable amount of time, it still does not have the segment starting at byte 400. But the server can still acknowledge the data that it has received. It can send back an ACK message with 400 as the acknowledgement number. This is saying that it expects data starting at byte 400 next. This is a really simple method of error control. It's not completely efficient, as every frame from byte 400 is resent. And this is just one way that error control can work. There are other methods. One example is selective acknowledgement, or SAC, which doesn't need to resend all the segments. Right now though, the important thing is not to learn all the error control messages, but to remember that TCP uses error recovery and UDP does not. If errors are becoming frequent, TCP can adapt with a type of flow control. What it will do is dynamically change the window size. We've seen that the 3-way handshake initializes values like port numbers, the ISN, and the window size. We've also seen that the window size is the amount of data a device can send before requiring an acknowledgement. So, the 3-way handshake is where they agree on the initial window size. But the window size isn't just set between 2 devices. It's set for each connection, and each connection can have a different size. Each connection can change over time too, which is why it's often called a sliding window or a dynamic window. Okay, that's nice and all, but what's the point? The point is that the receiver can tell the sender to send more information or less information per acknowledgement. Let's think about when a connection first starts. The devices at either end do not know how reliable the network path really is. Hopefully it's a rock-solid reliable connection that rarely drops any data at all. But it could also be a very flaky connection that regularly drops data. To deal with this, they may start with a relatively small window size, let's say 8 kilobytes. Remember that this means the sender can send up to 8 kilobytes of data before the receiver needs to acknowledge it. Now, if this goes well, that is to say, if this is a reliable connection with very little or no data loss, they may decide to increase their maximum window size. Maybe they'll put it up to 16 kilobytes. If it continues to go well, they may take it to 32, and then 64. The original TCP protocol would consider 64 to be the largest window size, but newer implementations can go even higher than that. On the other hand, what if the connection was losing data? A large window size would not be good here. Remember that error control in some TCP implementations will resend everything from the point where data was lost? A large window would mean that there's a lot of unnecessary retransmissions. So instead, the window will shrink. Data is acknowledged more often, and hopefully there are fewer retransmissions. A receiver could also use windows to signal the sender that it's overwhelmed. It could set the window size to 0, which would effectively pause the sender, giving the receiver time to catch up. Obviously, that's not ideal, and it's a symptom of a much larger problem. We've talked about the OSI and TCP IP models. Now we're going to focus on two of the protocols in the transport layer. These are TCP and UDP. We're going to see how they get information from one application to another, and their different approaches to their job. Two devices on a network rely on IP to deliver information between each other. This happens at layer 3, which may include routing packets across several networks. At layer 4, though, we see very different behavior. The transport layer doesn't care too much about the networks in between. Why? It doesn't need to. That's layer 3's job. It also doesn't care too much about the devices themselves. Instead, it cares more about getting data between applications. The two protocols that are responsible for this are TCP and UDP. They share a few things in common. For example, they both have headers and they both have port numbers. But as you can see in the headers, there's a lot more going on with TCP than UDP. That's because TCP supports a lot of features, while UDP is extremely lightweight. Through the rest of this video, we're going to see how TCP and UDP have different approaches to getting the job done, and why some applications will use one protocol or the other. In the header, you'll see fields for the source and destination ports. The ports are used to identify the applications on each device. In this way, ports are like addresses for applications. This is similar to how the devices themselves have IP addresses. When an application starts a conversation, it chooses a protocol to use as well as a random source port. This is some value from 1024 to 65,535. The exact number is generally not too important. The important part is that this port number is not already in use on the device. One port number cannot be given to more than one process at a time. The destination port number, that is the port number of the server application, is usually a well-known value. For example, if we were using HTTP for web browsing, the port will normally be port 80. Well-known ports are in the 0 to 1023 range. By making a port well-known, it's easy for the client to guess what port the destination application will use. If you want to see some well-known ports, have a look at the list in this URL. Of course, a server application could be configured to use a non-standard port, maybe port 81 for HTTP, for example. And this is fine, but the client can't guess the port number anymore. The client application will need to be manually configured to support this. Using different ports gives us a really useful feature called multiplexing. Multiplexing is a way for one host to have several applications accessing the network at once. They all share the one network card, the one network stack, the one IP address, but they each use different ports. Think of our client over here on the left. It already has a web browser open with a connection to a web server. Now it opens a mail client and is able to send and receive mail. Both applications can access the network at the same time. But when data arrives at this device, how does it know which application it belongs to? The IP and the MAC address are the same, so they won't help. Yeah, you guessed it. The two applications use different port numbers. A network application uses a concept called a socket. The exact definition of what a socket is will vary a little, but most agree that it is made up of a local IP address, a local port number, and a protocol. The protocol being either TCP or UDP. As port numbers are unique, so are sockets. Therefore, a socket can identify which application the network data belongs to. That's fairly straightforward so far, but it gets more interesting. A single application, like our web server software over here, can also access the network many times at once. But as this is only one application, it only has one port and one IP. The socket details are the same for all incoming connections. So how can it tell one from the other? It needs to look at the combination of the local socket information and the remote socket information. It can find all of this in the layer 3 and layer 4 headers. It now has 5 pieces of information: the local IP, the local port, the remote IP, the remote port, and the protocol. This combination of details is often called the 5-tuple. Each conversation is now truly unique. Let's have a quick look at this on a workstation. I'm using Windows here, but Linux, Mac, and other devices all use the same principles. Here we have a list of processes. Each process has a process ID, shown here in the PID column. These processes all make up applications. Some applications have one process, while others, like Chrome, have several. Some of these processes will be accessing the network. That means they'll have either a TCP or a UDP port assigned. And we can find this from the command line with the command netstat using the ANO flags. A shows all connections, N shows IP addresses instead of host names, and O shows the process ID that owns the connection. Looking at these processes, we can see whether they're using TCP or UDP, the local IP address and port number, the remote IP and port, the state that the connection is in, and the process number, which we can match up on the list we looked at earlier. Everything we've seen so far has been common to both TCP and UDP, but as you can see from the headers, they're quite different. This is because UDP was assigned to be very lightweight, while TCP was designed with a lot of extra features. For example, TCP is connection-oriented, while UDP is connectionless. Connection-oriented means that TCP will build and track a connection between applications on a pair of hosts before sending data. When they're done, TCP will close this connection. This stateful connection enables more features, like error recovery and flow control. There's a lot to understand around TCP connections, so we'll use the next video to go into those in detail. UDP, on the other hand, doesn't try to build a connection. It just starts sending data without worrying about any of those details. TCP and UDP also have very different feelings on what to do about errors. UDP, for one, doesn't care about errors. If a packet or segment goes missing, UDP doesn't worry, it just moves on to the next piece of data. TCP, though, does care about lost data. The receiver must acknowledge that all the data that it has received, and if data is lost, TCP will manage the retransmission. Because of this, TCP is known as reliable, while UDP is known as unreliable. This also leads into a TCP feature called windowing. This is where both sides of the conversation agree on how much data can be sent at once before requiring the receiver to acknowledge it. This value is called the window size. If there is no data loss, the window size can dynamically grow. If there is data loss, the window size will dynamically shrink. I'm not going to go into much detail on error recovery and windowing right now, because they've got their own video coming up very soon. The final difference I want to mention at this point is ordered data transfer. TCP uses sequence numbers in the header to track the order that segments should be processed in. This may be critical for some applications, but it does add extra overhead in processing time. This is not important for other applications, which may be why they use UDP. UDP does not care about the order the data's in. You may be wondering what UDP is even used for, as it seems to lack some critical features. After all, there's no error recovery. Isn't that quite important? It may sound silly to give up features like that, but there are some cases where this helps. Think about real-time applications like voice and video streaming. Imagine that one person on the phone call has network problems and a few seconds of data go missing. If TCP was being used here, this would be noticed and the missing data would need to be resent. While this is happening, the phone call is still going on. Now one of our callers is lagging behind. Do you see how that could be a problem? So instead, voice traffic uses UDP. If some data is lost, there are no retransmissions. They just move on and continue the rest of the phone call. So you can see that TCP and UDP are used for different purposes. UDP is lightweight, it has smaller headers, no retransmissions, and no flow control. It's great for real-time applications like voice or video, or for applications that manage these features themselves, like DNS, which we'll talk about some other time. TCP, on the other hand, has a full feature set, for applications that would rather leave these details up to the network stack. We're going to come forward a few decades now to a time when computers are starting to be more common in offices. They started as standalone computers, but they needed to share data, so networking functions had to be added. But unlike the old telephones, creating manual circuits or using physical cables between every single computer was not an option. One solution that they came up with was to daisy chain every computer together. It could be open-ended, which is called a bus topology, or the ends could be connected to form a loop, which is called a ring topology. And this is okay for a small number of computers, but it gets difficult when the number of computers in the office starts to grow. Imagine trying to add a new computer somewhere in the middle. We'd have to break the network apart and insert the computer in there. Also, if there's a break in the cable, the network has now been broken into two separate parts. And in addition to the physical connections, there needs to be a protocol. We've talked about these before. The protocol is an intelligent way of sending data from one location to another, without needing physical circuits like the old phone system. For example, the protocol needs to work out how to share this network, how to take turns sending messages, and how to work out which messages go where. And on top of all this, the network needs to figure out how to handle errors. What happens if two computers transmit at the same time and their messages get all mixed up? This specific scenario is called a collision, and it is a real concern when sharing the physical medium like we see here. Ethernet is a very common protocol, and we've spoken about this before too, but now it's time to add more detail. Ethernet uses MAC addresses to identify each computer on the network. There is one MAC address per network interface, so a router, for example, with more than one interface will have more than one MAC. Each MAC address is always 48 bits long, and it is written in hexadecimal. There are different ways you could write down a MAC address. Both of these that you see here are exactly the same address. They're just written down differently. The addresses are burned into the network card, so they're not something that we can change. This helps to make them unique, which is absolutely required for MAC addresses. To make this work, they're broken into two halves. The first 24 bits is called the OUI, or Organizationally Unique Identifier. And there's an organization out there called the IEEE, and it assigns this OUI portion of the MAC address to the hardware manufacturers. The manufacturers then assign the second half of this address to their products as they see fit. The point behind all this is that there is no two devices, or should be no two devices, across the entire world that have the same MAC address. Now, aside from these MAC addresses, there are also some special addresses. The first is the broadcast address, which is all Fs. No device owns this address. It just simply means deliver this frame to every device on the local network. I say local network, as routers will not forward broadcast frames to other networks. Another type of address is a multicast address. There are a lot of these, so I can't list them all, but you can look them up if you want to. These are also not owned by one particular device. They are used to send frames to a group of devices for a particular purpose. Multicast in general is something that we'll look at in a different video. Ethernet frames follow a well-known format that look like this. There's always a header before the data and always a trailer after. The source and destination are probably the most interesting fields. When a frame is sent, the sender embeds its own source address. And of course, it will have to put the destination address in there too. At the very start of the header is the preamble. This is a fixed pattern of ones and zeros, which lasts for 7 bytes, and this pattern shows that this is the start of the frame. The 8th byte is the SFD, or start frame delimiter. This is also a pattern, although a different one. It is 1 byte long, and that shows that the very next byte will be the destination address. The type field tells us which protocol is in the data section of the frame. Remember encapsulation that we've talked about a few times already? Well, this tells us which protocol has been encapsulated inside this Ethernet frame. These days, these are most likely going to be IPv4 or IPv6. IPv4 is probably the one you're more familiar with, and we'll look into IPv6 some more in some future videos. And at the very end of the frame is a trailer, and this trailer contains the frame check sequence, or FCS. This is used to determine if any part of the frame has become corrupted during transit. When the frame is first assembled, the sender will run a mathematical formula over the frame contents. It takes the result of this and puts it in the trailer. When the frame arrives, the receiver runs the same formula over the contents of the frame, without the trailer, of course. If the result matches the contents of the trailer, then clearly the data is the same as it was when it was first sent. That means there's been no corruption. But if the results are different, then there must have been a change in the data somewhere. That means that the frame is corrupt and it will be discarded. Ethernet will not try to recover this data. However, as we've seen in past videos, higher level protocols like TCP may try to recover the data. In this older style of network, when frames are sent, every device will receive a copy. When a device receives the frame, it will look at the destination MAC address in the Ethernet header. If it owns that address, it will accept and process the frame. If not, it should discard the frame. This raises two problems. Firstly, there's a lot of unnecessary traffic flowing around which uses up more resources. Secondly, this has potential to be a security risk. If every device can see your traffic, then they might also be able to see your private information. The older networks have their limitations, as we've discussed. So around the mid-80s, the idea of a hub was introduced, much like the one we're showing here. This is probably getting a lot closer to what you're used to seeing. It's a box that you can connect your computer to, rather than needing to chain all your computers up. This makes it so much easier to add and remove devices as you need to. And if you run out of ports, you can buy an extra hub and you can daisy chain those to get the extra ports you need. On the inside, hubs aren't really doing anything different. They're still using the same bus network, connecting all the ports in a chain. That means that the ports are part of the same LAN and any data received on one port is sent to all the other ports. For this reason, hubs are sometimes called port repeaters. So there's a lot of extra traffic flowing around, and every device can see every other device's traffic. Hubs were definitely an improvement, but they haven't added any intelligence or data processing. From a network perspective, they're not much more than a bundle of wires put inside a box, and that makes them layer 1 devices. And as this is still a bus network inside the hub, a device cannot send and receive at the same time. We have a term for this, and that is half duplex. For that matter, only one device on the network can send at one time. If two devices try to send at the same time, they cause a collision. And because a collision could happen at any point in this topology, the entire network that we're looking at is called a collision domain. And the larger the network, the larger the collision domain. That is, the more devices, the more chances there are of a collision occurring. And the more collisions that happen mean we need to spend more time waiting and resending frames, and that lowers the overall performance of the network. Sadly, in a network like this, we can't just eliminate collisions. But Ethernet, being very clever as it is, can minimize them. And to do this, it uses, an algorithm or maybe a protocol called Carrier Sense Multiple Access, or CSMA. There are two parts to this. First, collision avoidance. It attempts to determine when the network is idle, and it will only transmit then. This helps to avoid a lot of collisions before they even happen. But on occasion, two devices will determine that the network is idle, and at the exact same time, they will try to transmit. And yes, you guessed it, that causes a collision. So, the second part is collision detection, which is able to, just as it sounds, detect these collisions. When the two devices detect the collision, they both decide to wait a short random amount of time before attempting again. And because these times are random, they shouldn't be the same, which lowers the chance of them both transmitting at once, which lowers the chance of collisions. Well, we've seen that hubs were an improvement, but they still do have some downsides. All devices are in the same collision domain. They use half-duplex communication, and data is sent out every single port. All this adds up to limiting how far the network can grow. So, to address some of these concerns, network bridges were created. We can take our large bus topology network, and we can break it into 2 or more smaller networks. We then connect them using a bridge. The bridge is a physical device that would look very much like a hub, maybe with fewer ports. Typically, hubs would connect to bridges, and other devices would connect to the hubs. While all of this is still in one network, or LAN, we have now broken this into smaller segments. Unlike hubs, bridges have a bit of intelligence. They keep a table of the network's MAC addresses in memory, as well as which segment these MAC addresses belong to. When a frame arrives at a bridge interface, the bridge looks at the destination MAC field in the Ethernet header. It will then look at its MAC table, and it will see which network segment this MAC belongs to. It knows about each segment as it has an interface connected to each one. If the MAC address is in the same segment that a frame came from, it will not forward the frame on. It assumes that the sender is already closer to the destination than it is, so it doesn't need to forward the frame on. If the MAC address for the destination devices is on a different network segment, the bridge will forward the frame out. If there's a hub connected, that then will of course replicate its frame to all of its ports as normal, and the destination will ultimately get the frame. This process really cuts down on the amount of data that's flooded through the network. It also breaks one large collision domain into a few smaller collision domains. And remember that the smaller the collision domain, the better, as there's a smaller chance of collisions, and less collisions means better performance. The network as a whole can now grow larger than before. The term we use for this is scalability. And because bridges are intelligent, and they look at the MAC addresses, these are layer 2 devices. Now if you're really thinking, you will be wondering, how does a bridge know where all these MAC addresses are? And that's a very good question. I'm so glad you asked. The bridge doesn't just magically know where all these addresses are. It needs to learn them. So let's just imagine that the bridge in this diagram here has just been turned on. Right now, there are no entries in the MAC table. So a device sends out a frame and it arrives at the bridge. The bridge does a MAC lookup on both the source and the destination MAC addresses, and it finds that neither are in its table yet. So the first thing it will do is it will add the source MAC address to the table, as now it knows where to find the device that owns that address. The destination is still unknown. So, without this information, the bridge has no choice but to flood the frame out all interfaces. That is, except the one that the frame was received on. Let's say that the destination is in the network to the right, and it has now received the frame. It wants to respond by sending a frame of its own, and that arrives at the bridge. The bridge does a MAC table lookup just like it did before, and it sees a new source address, which it learns. Fortunately, now it already knows where the destination MAC is, as it had learned it earlier, and it can send it out the correct interface, avoiding the need to flood the frame everywhere. Sending the frame out is called forwarding. Being selective and not forwarding it out every single interface is called filtering. Let's imagine though that we've picked up a computer and moved it from one segment to another. What problems might we face here? The problem is that the entry in the MAC table is now incorrect. From this we can see that the MAC table entries should not be permanent. The next time it sends a frame, the bridge will see the MAC address on a different interface and it will update the entry in the table. Take careful note of this. A MAC address can only be learned on one single interface. And what would happen if we turn the device off? Or perhaps it's failed, or it was a guest laptop connected to our network. Well, each entry in the table has an aging timer. When the MAC address is learned, this timer starts counting. Whenever traffic from the device is seen, the timer resets. If no traffic is seen before the timer expires, the entry will be removed from the table. This helps keep the table nice and small. After all, these tables have a limit to their size as well. In summary, bridges have 5 very important functions. They flood traffic out their interfaces if they don't know where to send it. They learn which interfaces to use for certain destinations, and they forward traffic on these interfaces. They filter traffic from interfaces that they don't need to send the traffic on, and they age out entries in the MAC table as they become stale. I highly recommend that you try to remember these functions, especially if you're planning on doing a networking exam. Now, let's move completely into modern networking. Around the mid-1990s, switching was developed, and it became popular by around the year 2000. Switches are the devices that we use today. They bring the best features of hubs and bridges together into a single device. They have a lot of ports like hubs do, so we would typically connect devices directly into the switches. There's also no dumb bus topology inside the switches either. Every single port behaves like a bridge port, so this topology is no longer a bus topology, but a star topology. This also means that frames do not get flooded out the ports as often. In addition to this, switches are intelligent and they support the same functions that bridges do, like learning, forwarding, aging, and so on. Like bridges, as they're intelligent and look at the MAC addresses, they operate at layer 2. A very special advantage to this is that every single port is part of a separate collision domain. That now means that multiple devices can send at one time, and there's very little chance of collisions anymore. This vastly improves efficiency and performance. And for that matter, this isn't a shared bus network. Devices can send and receive at the same time, which we call full duplex. Keep in mind though that if you take an old hub, if you can even find one anymore, and you connect it to a switch port, then everything on that hub, it's still part of the same collision domain. It's still half duplex and so on. The important thing to learn from this is don't use hubs, use switches. The switches handle frames in 3 different possible ways. The first method is called store and forward. The first few bits of a frame arrive at the switch, and the switch stores them in memory. In fact, it will keep storing these bits in memory until the entire frame has arrived. Once it's fully there, it will then send the frame out one of its ports. Store and forward is the safe switching method, as the entire frame can be checked for errors before it's sent out. The second method is called cut through. The switch starts receiving a few bits of a frame and it waits just long enough to see the destination MAC address. Once it's got the address, it does the required lookups to work out which interface to use, and then will immediately start forwarding out the bits. This method does not use any form of error checking, at least not by the switch. All the error checking is left up to the destination device. This makes it by far the fastest method of switching. The third method is a compromise between these two. It's called fragment-free. The switch stores the first 64 bits of the frame as they're received because this is the part that's most likely to have errors. If there aren't any errors here, then all the bits are sent out immediately as soon as they're received. Generally, we don't choose what type of switching we use. It's chosen by the manufacturer of the switch themselves. It's not something that you generally think about every day. It might be something you think about if you're buying a switch though. So, what do you think? Why do we call these switches? I kind of think it's like having an old telephone switchboard operator in a little box. When frames come in, they create the path for these frames to take, just like they did with old telephone calls. And really, that's what switching is all about. It's about dynamically creating paths to forward frames. Hubs are pretty rare these days too. Bridges are still around, but they're a bit different to what I've described here. These days, really, switching is If the company we work for grows, then they're going to need more computers, printers, servers, and other devices. These all connect to the network, which means they all need more switch ports to connect to. So eventually we buy more switches. Normally we would connect one switch to another to extend our number of ports, but we've cut our network into VLANs now. So how do we connect the two switches together? Should we perhaps run a link between each switch for each VLAN? Well, we could. We could make that work. But what happens if we have many VLANs? If we need a link for each VLAN, we will use up our ports again pretty quickly, leaving less for the new devices that we need to connect. And then what happens if we want to add a third switch? Or a fourth? Clearly this method is not scalable, meaning that its growth is severely limited. Instead, we are able to use a single link, which is capable of carrying all of our VLANs. This uses a technology called trunking or tagging. In the last video, we saw how to add devices to a VLAN. The type of port they connect to is called an access port. Typically, we would connect workstations, printers, servers, and phones to an access port. This will have one data VLAN and maybe one additional VLAN for voice, which I'll talk about in a minute. When we connect two switches together, we configure these ports as trunk ports. Trunk ports are able to have many VLANs configured on them at one time. If you have trouble remembering the difference, an access port is how workstations access the network. Trunk ports are like a single tree trunk with many branches or VLANs. So we're left with an interesting question. Why do we want to use VLANs to separate traffic if a trunk link just mixes them all together again? Well, let me give you some good news. The traffic doesn't fully get mixed together. It goes over the same link, sure, but it won't leave its VLAN. This is thanks to our good friend Ethernet. As a reminder, here's the Ethernet header. Think of a device on a VLAN sending a frame. It goes to an access port, which is configured with a VLAN, so the switch knows which VLAN this frame belongs to. When the frame reaches the trunk link, the switch will add a 4-byte tag to the Ethernet header. The tag contains a few different types of information, but the only part we care about right now is the VLAN ID. Please note it's just the VLAN ID, and not the VLAN name that we configured in the last lab. This means that VLAN names are locally significant to each switch, and they don't have to match on two different switches. When the frame arrives at the destination trunk port, the switch looks at the tag and knows the VLAN that this frame belongs to. It can now strip the tag from the frame and deliver it to the destination workstation. So the workstation will never see the VLAN tag. In fact, it doesn't really even know that it's in a VLAN. And here is a key point for you. A trunk link extends VLANs from one switch to another. As VLANs are in a broadcast domain, trunk links also extend broadcast domains across switches. So broadcast messages will stay within a VLAN, but will pass over a trunk to other switches. And the same is true for flooding. Any frame that needs to be flooded will stay within the VLAN, but will travel over the trunk links to other switches. And once again, Cisco's terminology is a little bit different to everyone else's. To start with, a trunk port is really a tagged port. This is because of the tag that is added to the frame as it passes between the switches. Also, an access port is really an untagged port. Remember how I said that there is no tag in the Ethernet frame when it was delivered to the workstation? That's why it's called an untagged port. Don't worry too much about which terminology you use. They're both really well known. It's still a good idea to understand both, so you'll always know what other people are talking about though. When it comes to tagging, there are two ways it can be done. The first is called 802.1q, which was developed by the IEEE. Everyone supports this standard, and this is what I've been describing so far. Because this is an IEEE standard, all switches can use it, which means a trunk between switches from different manufacturers is possible. The second possibility is called ISL, or Inter-Switch Link. This is Cisco's original trunking standard and is much older than 802.1q. This one's getting pretty rare these days. In fact, I've never actually seen it in production myself. But you do still see it mentioned in some documentation, and you can still configure it on some switches, so you need to be aware that it's out there. But in most cases, forget ISL and focus on 802.1q. Earlier, I mentioned voice VLANs. These are important if you have IP telephony in your network. If you're not familiar with that term, IP telephony is where you have phones connected to your network. In a case like this, you would probably have a phone and a workstation on each desk. Your workstation would belong to a data VLAN, while the phone would belong to a voice VLAN. So based on what we've talked about so far, you would probably connect the workstation to one port on the switch, and the phone to another. But usually, phones are a little bit special. They have a miniature 3-port switch built in, so we can connect the phone to the switch, and the workstation to the phone. The third port is hidden from sight, it's inside the phone, connecting to the phone hardware. Why would we do this? Well, there's 2 reasons. For one, there's less need for ports in the main switch. Secondly, you don't normally connect phones and workstations directly into a switch. They normally go into a wall socket, with cabling through the wall, which is eventually connected to the switch. So with less connections to the switch, there's less need for cabling, which can be expensive to install. Anyway, the link from the phone to the switch is like a mini trunk link, except it carries only 2 VLANs, the data VLAN and the voice VLAN. When you first turn on a switch, all the ports will, by default, belong to VLAN 1. We don't do anything to configure VLAN 1, it's just always there. So is VLAN 1 special in any way? The answer is a little bit tricky. But on a Cisco switch, VLAN 1 is indeed a little bit special. From time to time, there is a need to pass control traffic between devices. So I'm not talking about a workstation sending traffic through a switch here. I'm talking about a case when 2 switches are connected together, like in our lab. We're going to see this a bit later on with an example protocol called CDP. But the key point here is that control traffic between Cisco switches use VLAN 1. Keep in mind that other switch vendors may have a different way of approaching this. So don't try to remove VLAN 1. I don't even think you can remove VLAN 1 now I think about it. Also, it's a good practice to keep your devices, like your workstations and printers and so on a separate VLAN. Just leave VLAN 1 for this control traffic. There's another special VLAN that we need to consider. This is called the native VLAN. The native VLAN was created to support devices that don't support VLANs. Think of a hub or a cheap switch, for example. If you connect one of these devices to a trunk link, they won't be able to tag any of the traffic they send. So which VLAN is this traffic a part of? The answer is the native VLAN. By default, the native VLAN is VLAN 1, but we can change this to another VLAN if we want to. In fact, we'll see this in a lab soon. But before that, consider what happens if traffic passes from a switch to a hub. Any frames that are part of the native VLAN will be sent out untagged. This keeps compatibility with these non-VLAN enabled devices. Now, in the last video, we connected a router to each VLAN to enable workstations and servers to communicate. There were 2 VLANs, so we used 2 links. But what if we have 10 VLANs? Do we need 10 ports on our router? Does our router even have 10 ports? What if we needed 30 VLANs? This is the same concern we faced with our switches earlier. We solved this by using a trunk link. The good news is that routers can also use trunk links. This might sound surprising, as trunking is a switching technology, but you'll find that the lines between routers and switches are sometimes blurry. Routers will support some switching functions, like trunking, and switches will support some routing functions too. but they still behave a little bit differently. Routers primarily deal with routing, which means their interfaces need IP addresses. This is what the workstations and servers will use as their default gateway. But how can we put an IP address in each VLAN? How does the router know which IP address belongs in each VLAN? The answer may surprise you. The router's physical interface is connected to the switch, but the physical interface can be divided up into several virtual sub-interfaces. This is very similar to how we divided our switch into several VLANs. On a router, we divide up interfaces and we map each one to a different VLAN. And once we have several virtual interfaces, we configure them independently. This includes different IPs for each one. And these interfaces, even though they're virtual, still behave like regular interfaces, so we can still use them to route traffic between VLANs. This way of configuring the router is called Router on a Stick, or ROAS. It's called this because the single trunk link between the router and switch looks a bit like a stick. Picture this. You have a small network with one switch and a few devices connected. Perhaps some workstations, printers, and a router connected to the internet. As the business grows, you need to add more equipment, so you add a second switch. This is, of course, connected to the first switch. This is all still one single VLAN and one subnet at this point. We're just increasing the number of available ports. Now let's say we grow a bit more and add a third switch. Of course, we'll want to link this to our other two switches. This is still all one VLAN and one subnet, just extra ports that we can use. It might not be obvious, but this presents us with a problem. Consider what happens when a device on the network sends a frame to the switch. You'll remember from earlier videos that switches learn MAC addresses of connected devices, so it knows exactly where to send these frames. Broadcasts, however, are a bit different. They are sent out all switch ports on the VLAN, except the port the frame was received on. This includes links to other switches. Do you see the problem that we might face here? Take a look at what happens to the broadcast frame. The switch forwards the frame out of each port, including the uplinks to the other switches. These switches forward the frame out their ports too. The broadcast frame begins looping around the network indefinitely. Remember that frames operate at layer 2, not layer 3 like packets do. There's nothing built in at layer 2 to stop frames from looping around. But surely that's not too bad, right? A frame loops around for a bit, it can't be that bad. Look what happens when we add a fourth switch. This causes a single broadcast frame to be duplicated many times, each one looping around indefinitely. What if we now add more hosts to the network? Even with just 4 hosts, this is getting out of control. Of course, with 4 switches, we could have 100 hosts, and a 4-switch network isn't even all that big. We call this a broadcast storm. These frames will continue to loop and duplicate until the switches can't handle any more traffic. At this point, the network grinds to a halt. It's a pretty big problem now, isn't it? This is where spanning tree protocol comes in. This is a relatively old protocol developed by Radia Perlman in 1985. It is a process that runs on every switch, detects potential loops, and strategically disables certain links, making the network loop-free. But you may be wondering, why bother cabling up these extra links if spanning tree is just going to block them anyway? Well, there are 2 reasons. Firstly, spanning tree is clever enough to select the most appropriate link to block, which might not be the one you are expecting. Second, if we lose one of our switches or other links, spanning tree can re-enable the blocked link, repairing the network. The key points to remember right now are: spanning tree works at layer 2. Layer 2 does not have any built-in loop prevention. Layer 3 does have loop prevention. This is the time to live field in the IP header. Here you can see the benefit to really understanding the lower levels of the OSI model. This doesn't seem too hard so far, right? But this has been a simple topology. A complicated topology is where spanning tree really earns its money. Have a look at this network, which to be fair isn't really overly complicated. Here we see several loops. Once again, spanning tree goes through the topology and finds the loops. It will then select the most appropriate link to disable, eliminating the loop. The most appropriate link is usually the slowest link. Spanning tree prevents layer 2 loops in our network. It does this by finding potential loops and then blocking one of the links to stop the loop from forming. Let's see how it does this. To start with, spanning tree running on one switch needs to discover other connected switches and share information with them. It will send out a special frame called a Bridge Protocol Data Unit, or BPDU. There are two types of BPDUs. This one is called a configuration BPDU. Initially, these messages enable switches to learn if there are any other spanning tree enabled switches nearby. Did you notice that we started with a single switch and worked our way out from there? In a spanning tree topology, one switch is nominated to be the root bridge. Spanning tree is better thought of, as the name suggests, a tree shape, or maybe an inverted tree shape. At the very top of this tree is the root bridge. Let's focus our attention on the root bridge for now. The root bridge will send configuration BPDUs outward to other switches. These are sent out on all ports by default. Other switches may send BPDUs to the root bridge too. This depends on the version, which we'll discuss briefly later. The root bridge assigns roles to its ports that connect to other switches. Ports that face away from the root bridge are called designated ports. Other switches have some ports facing toward the root bridge and some ports facing away. One port on each switch, the one closest to the root bridge, is called the root port. The root bridge can't have ports facing itself, so it never has any root ports. Ports facing away from the root bridge are the designated ports. But wait, a loop has formed in the network. Spanning tree needs to do something about this. First, it needs to detect this loop. But how? Let's take a step back. When a switch sends a BPDU, it will put a bridge ID in there. This ID is unique to each switch. So imagine now that the root bridge is sending configuration BPDUs to its connected switches. In our example so far, there's two of them. They receive these BPDUs and know they're connected to the root bridge. As part of the spanning tree process, they also forward these BPDUs onto other switches. So in our example, these two switches will forward these BPDUs to each other. Now they will independently be able to see that they have two paths to the root bridge. There should only be one, so this is how they know that there's a loop. It is at this point that each switch needs to decide which ports are root ports. Remember that each switch makes its own independent decisions based on what it has learned. As we have said a few times, the root bridge doesn't have any root ports, so that part's easy. It makes all of its ports designated ports. It's a little bit more complicated for the other switches. Each port has a cost, which is based on the speed of the link. The higher the link speed, the lower the cost. So for now, let's say that the cost of each of these ports is 4. That's not very helpful yet, as they're all the same. The useful part is that the switch measures the total cost to reach the root bridge. Think about the root bridge sending BPDUs again. The two switches receive the BPDU and decide that the cost to get to the root bridge over these links is 4. These switches update the BPDU with the cost of 4 and send them out the other interfaces. So when these BPDUs are received, the switch adds the cost written in the BPDU message to the cost of the interface it was received on. In this example, the cost to get to the root bridge, using these paths, is 8. The best path to the root bridge is now clear. These ports become the root ports. It's also clear which link should be disabled to prevent this loop. But how is it done? Do both these switches disable their ports, or does just one of them do it? The short answer is, only one end of the link will be disabled, and the end that's selected comes down to the bridge ID once again. The one with the lowest bridge ID will set its port to designated. The other will set its port in a blocking state. These three switches have now fully converged and can forward traffic without the risk of looping and broadcast storms. Of course, this process needs to happen throughout the entire network, which can get more complicated as we move through. Does it end here? No, the root bridge will continue to send BPDUs out regularly. The other switches will continue to update the cost and forward them out. This mechanism is like a heartbeat. It tells the switches that they have a valid path through to the root bridge. If the BPDUs suddenly go missing, then there is probably a dead switch or link somewhere. But what happens if a switch dies? Firstly, it won't be forwarding BPDUs anymore. Nearby switches will notice the loss of BPDUs and know that the switch is gone. The spanning tree topology then goes through a reconvergence process. Switches may need to update their port types. But there are other changes that can happen in a network. We might add a new switch or link. This would also cause reconvergence, and the port types could change again. Basically, anything that causes a spanning tree port to go up or down, or change the flow of BPDUs, will cause reconvergence. The next step is to think about how the rest of the network learns about these changes. This does not just rely on the configuration BPDUs that the root bridge sends. There is a second type of BPDU called a Topology Change Notification, or TCN. These are sent by regular switches, not the root bridge. TCNs are sent only when there's a change in the topology. If a switch receives a TCN, it will generate its own TCN and forward it on. Eventually this filters through to the root bridge. At this point, the root bridge will update its configuration BPDUs if necessary. These continue to be sent out regularly as normal. The process of flooding BPDUs, finding loops, and selecting ports is not instant. You might be wondering then, how does spanning tree prevent loops before this process has completed? Well, by default, every port on a switch goes through a particular process before it fully comes up. This lets the switch decide if any given port is connected to an end device, like a printer or workstation, or if it's connected to another switch. A loop can't form on a port connected to an end device, but it can on a switch-to-switch link. So when the port first comes up, probably because we've enabled it or plugged something in, it will start in the blocking state. This stops the loops from forming right away as no data can pass. The only exception to this is BPDUs, which are allowed to flow. By default, the port will remain in this state for 20 seconds. Next, the port moves into the listening state. A port in the listening state can be a root or designated port. While in this state, the switch will process any BPDUs it receives in order to learn about the network. This may cause the port to transition back to blocking if needed. Regular data still does not pass through this port yet. The listening state lasts for 15 seconds. Keep in mind that this is happening for all ports, not just ports connected to other switches. After the listening state, the port moves to the learning state. During this state, the switch does what all switches do all the time. It learns MAC addresses and builds the MAC address table. This state lasts for 15 seconds, and still regular data cannot pass through this port. Finally, the port transitions to the forwarding state, and regular data can now flow. The port will remain in this state until some topology change requires it to go through the process again. As I said in the last video, spanning tree has been around for a long time, at least in IT. Everything we've been discussing so far is the original spanning tree standard, also called 802.1d or classic spanning tree. But there's a few downsides to classic spanning tree. We saw one just a moment ago when we realized that it took 50 seconds for the port to come up. So to address this and a few other issues, some newer versions of spanning tree were developed. We're going to take a brief look at these improvements. First up, Cisco released per VLAN spanning tree as a proprietary solution. Classic spanning tree will block links for all VLANs at once, but PVST treats VLANs individually. This means that, for example, one link may be blocked for VLAN 1, but a different link will be blocked for VLAN 2. This means that the network can be used a bit more efficiently, as you don't have entire links sitting around idle. Later, they updated this to PVST+, so it could be compatible with classic spanning tree and therefore with other vendors. They also added some enhancements that would treat end device ports differently to ports that connect to other switches. so you wouldn't have to wait 50 seconds for your workstation or printer to come online. The next standard to come along was Rapid Spanning Tree, or 802.1w. This was standards-based, so all vendors could use it. This standard still treats all VLANs the same, like classic spanning tree does, but it changes the way the port states work as well as their timers. It no longer takes 50 seconds to bring switch-to-switch links up. Cisco liked these changes, but they also liked the idea of treating VLANs individually, so they created another of their own standard. If you hadn't noticed, Cisco are kind of known for doing that. So they released Rapid Per VLAN Spanning Tree, all the advantages of RSTP and PVST in one protocol. Once again though, this is Cisco only, so other vendors can't use it. And finally, the rest of the industry caught up and created Multiple Spanning Tree, or 802.1s. MST is quick, like RSTP, but it handles VLANs better. In fact, it handles VLANs a little better than PVST and RPVST, as it considers groups of VLANs when creating spanning tree topologies, rather than considering each VLAN individually. This approach puts less strain on the switch and its resources. The whole point of routers is to route or forward traffic from one network to another. Sometimes packets have to be forwarded across many networks before they reach their destination. I say routers, but these days many switches are also capable of routing packets. They are called layer 3 switches or multi-layer switches, and as the name suggests, they're good for both routing and switching. Layer 3 switches are especially good for routing traffic between VLANs, while routers are often used when connecting to the internet or for WAN connections. In these videos, I'm just going to continue using the term router, but be aware that the principles can apply to layer 3 switches as well. Each router in the network will need to make its own decisions about how a packet should be forwarded. But before they can do this, they need to learn about paths through the network. They don't just magically know where everything is. As an example, if we open router R5 and try to ping an IP in a different network, we can see that it fails. To start with, they will know about any network they're directly connected to. These networks will be added to the routing table, which we can see with Show IP Route. All layer 3 devices will have a routing table, although they may look different depending on the vendor. Here we can see a list of networks with a code on the left. Anything with a C code is a directly connected network. If you forget what a particular code means, you can always look at the handy reference at the top. Next to the code is the network itself. The first part is the prefix, and the second part is the subnet mask, shown in CIDR notation. The information just to the right of that tells us that our router is directly connected to this network, and it tells us which interface is used. The other type of route we can see here is called a local route, which has an L code. These represent the router's IP addresses within the connected network. That means that there is one local route per connected route. Can you also see that each local route has a /32 mask? Subnet masks are 32 bits long, so a /32 mask has every bit turned on. So this refers to a single host. In the routing table, this is called a host route, as it is pointing to a single host rather than an entire network. Connected and local routes will appear in the routing table automatically when an active interface is configured with an IP address. You might also notice that the routing table has sections that are listed as either subnetted or variably subnetted. This goes back to the classful networking days. All this means is that the subnetted network is part of a larger classful network. To be honest, I don't really think about these things that much. As I've said in some other videos, there's not a lot of reason to think in terms of classes anymore. We can configure a static route to point the way. Here's the anatomy of a static route. It includes the destination network that we want to reach. This may be a nearby network or it could be some distance away. The subnet mask of the remote network. The next hop IP that we forward packets to. The next hop IP in most cases will be the IP address of another router in a network that our router is directly connected to. For example, router R5 may use the IP address of R3 as a next hop, as they both have interfaces in the 172.16.0.0 network. Maybe it's easier to see this in action. Let's configure R5 with a route so we can reach the 192.168.3.0 network. We use the IP route command, add in 192.168.3.0, give it the subnet mask of 255.255.255.0, and finally the next hop IP is 172.16.0.3. We're not limited to just one static route, of course. We can create many more. For example, a route to 172.16.30.60. Now let's take a look at that routing table again. See how there are now two new routes listed. They have an S code, which refers to a static route. A static route is one that we configure manually. The entry for a static route looks different to the connected and local routes. Next to the network and mask, we have the numbers 1/0 in square brackets, and I'll explain that one a little bit later. Further to the right, we have the IP address of the next hop. This is the IP that the router will forward packets to if it needs to send them to this network. While we're still talking about static routes, there is an alternative way that we can use them. If we want, we can configure an outgoing interface rather than a next hop IP. In cases like this, the router will use an ARP message to find the IP address of the next hop. This might be used in a case where we have a small network with only two routers in it. For example, like the small network between R1 and R2. Personally, I don't really like using these types of static routes very often. I much prefer using a next hop IP address, but you need to be aware that sometimes you will see them out there. I've already mentioned a few times that each router will make its own decisions about how to handle and forward packets. Let's take a little time to think about how it will make these decisions and how packets flow through the network. To start with, a host connected to the network will create a packet. If this needs to go to any network that it is not a part of, it will send the packet to its default gateway. Once the packet arrives at the router needs to decide what to do. Technically at this point it is a frame, not a packet, as it will still have a layer 2 header, probably Ethernet. So the first router will check to see if the frame is valid or corrupt. If it is corrupt, it will be discarded. If it's fine, it will decapsulate the frame, leaving a packet. It can now retrieve the destination IP address in the IP header and compare it to routes in the routing table. If there is a route, the router will prepare to forward the packet to the next hop. This includes getting the MAC address of the next hop and encapsulating the packet with new Ethernet headers and trailers. If there is no suitable route in the routing table, the router will drop the packet. Keep in mind though, that the router will not check if the next hop is up. If the next hop does not exist, the packet will be dropped. Hosts have a default gateway. Guess what? Routers do too. If a router does not have a route to a particular destination, it can use its default route. It's kind of a catch-all route that's used if nothing better can be found. The best example of when this is used is for your internet connection. In most networks, you can't reasonably be expected to have a route for every possible destination on the internet. So for this, you will have a default route. We can still configure this like any other route though. The difference is that the destination network is 0.0.0.0 with a subnet mask of 0.0.0.0.0. This will match everything, assuming that there's nothing more specific, of course. When we look at the routing table, we see this in two places. For one, it will show up as a regular route. The only difference is the star symbol. The star symbol means candidate default. You can have more than one default route configured if you want to, but the router will only use one at a time. So the candidate default is the one that the router is using right now. We also see this listed as the gateway of last resort. This is also the default route that is currently in use. That it's a pain to configure static routes everywhere. They have their place, of course, But if you're configuring a lot of them, it takes a lot of time, it's prone to mistakes, and they aren't very reactive to changes in the network. So now we're going to look at an alternative, dynamic routing. We can configure one or more dynamic routing protocols on each router, which enables the routers to learn about other routers within the network. Each router will share any route information that it knows with its neighbors, enabling each router to dynamically build their routing tables. There are a few different routing protocol options. Some are more advanced than others, depending on what you're trying to do. We're covering the basics in this video, and in the next we're going to try configuring Routing Information Protocol, or RIP. So why do we want our routing to be dynamic? So routers can react quickly to changes in the network. Imagine that one of our routers fails. Its neighboring routers will notice that it's dead and will find alternative paths through the network. That is, of course, as long as there is an alternative path to use. Another reason is complexity. Imagine that your network has many routers, maybe 100 or so. Do you want to configure static routing on each one? Do you want to reconfigure them all if something in the network changes? Of course not. Dynamic routing simplifies your configuration. But here's the thought. When dynamic routing is introduced, our routers might be learning routes from a few different sources of information. For example, we might have some routes learned from RIP, and some configured as static routes. So how does a router decide how to forward traffic? Well, the same rule still apply as before. The router will use its own routing table to make its own decisions. It will build its routing table based on information that its neighbors share, but it won't ask its neighbors what to do. It always makes its own decisions. But what if there are two valid routes in the routing table? Take these examples here, 10.120/24 and 10.0.0.0/8. Now these are both valid networks, and they are both different networks, so they both appear in the routing table. Now imagine that a packet arrives at this router. Its destination is 10.121. Can you see how this packet could match both of these routes? So what will our router do in this case? Here is the next rule that you need to know. The router will always use the longest matching route. That is, the route with the most specific subnet mask will be chosen. This is called longest prefix match, or LPM. In this example, the route for 10.120/24 is chosen as it has the 24-bit subnet mask. I can't stress enough how important this is to know. If you only take away one thing from this video, longest prefix matching should be your key point. We can occasionally use this rule to our advantage. On this router, we have a route to 10.120/24 going via 172.16.15.1, which we can prove with a trace route. Now what if we want to test a different path? We can add in a host route like this one, which has a longer subnet mask. Repeating the trace route shows that traffic is now taking a different path. We've just changed how routing works for one single IP address without affecting the rest. And now let me show you another useful trick. If you ever need to check which route is used for a particular IP, just add the IP to the show IP route command. And you can see from this that .1 is using a different route than .22, thanks to the host route we just configured. So here's another question. What happens if the router learns the same route from more than one source? For example, the router may get a route from RIP, OSPF, as well as having a static route configured. Which one goes into the routing table? In a case like this, the router uses a value called the administrative distance to decide which routes are used. Every source of routing information, whether RIP, OSPF, static routes, or whatever else, has an administrative distance. There's a few common ones shown here in this table. This is a value that tells the router how believable a particular source of information is. The lower the value, the more the router will trust it. This is important to know, so make sure you understand it. From this table, you can see that a static route is preferred over an OSPF route. OSPF is preferred to RIP, and so on. If a router learns the same route from both OSPF and RIP, and you manually configure the same route as the static route, the router will install the static route into the routing table. If you then remove the static route, the OSPF route would go in its place. Just keep in mind though that other vendors have slightly different names for administrative distance. They also have different values, but the concepts will be the same. Let's bring up a routing table again. You might remember from the last video that I said I'd explain the two numbers in the square brackets later. Well, the first one is the administrative distance. As you can see here, it is set to 1. If we want to, we can manipulate the administrative distance to our advantage. Take a look at the topology again. See how there are two paths between R1 and R5? Let's assume that one is a high-speed link and the other is a low-speed link. What we would like to do here is use the high-speed link under normal conditions. However, if this link fails, we'd like to use the low-speed link as a backup. On R5, we already have 3 routes to the 10.1 networks, and they're all using .1 as the next hop. We know that these will be removed from the routing table if the interface goes down. So what we'll do is configure a second set of routes, called floating static routes, as a backup. This is not much different to a regular static route. We use a different next hop IP, which is on the other link, and we add a different administrative distance to the end of the command, say 20 for example. Our regular routes have an AD of 1, so they will be added to the routing table under normal circumstances. If that interface goes down, the regular route will be removed, and this route with the higher administrative distance will be added instead. And just to prove it, if I break the primary link now, we can see that the new routes are now in the routing table. We know these are our backups as the administrative distance next to the route is 20, not the usual 1. RIP comes from the days when all addressing was classful. As we started moving away from classful addressing, RIP needed to be updated to version 2, which is now classless. The whole point of RIP and other dynamic routing protocols is to share routes with neighboring routers. This way, each router learns about routes to other parts of the network and can decide on the best way to get there. This can be used instead of or along with static routing. RIP, being a very simple routing protocol, is a very good place to start learning. The concepts learned here can be extended to other routing protocols like OSPF or EIGRP. But before we dive right into RIP configuration, let's talk about dynamic routing protocols in general. We can break routing protocols into 2 categories, distance vector and link state. These are 2 entirely different approaches to how a routing protocol works. At a high level, we can say that a router running a link state routing protocol builds a full map of the network. Each router shares information on each path they know about with their neighbors. These neighbors pass this information on to their neighbors, and so on. The result is that every router builds the same map of the network. Distance vector routing protocols, which includes RIP, takes a different approach. Routers running a distance vector protocol will still share routing information with their neighbors, but they won't share as much information and they won't build a full map. Simply put, they share a network and how far away it is. For example, a router might say, I know about 10, 10, 10, 0, and it is 2 hops away. In this example, the distance is how far away the network is, and the vector is the direction the network is in. The network direction, you might say. And that's how we get the name distance vector. This makes distance vector routing protocols less like a map and more like signposts pointing the way. If a router gets an update for the same network from 2 different neighbors, it will look at the distance and use the path that it thinks is better. We'll see this in detail soon. But for now, we should start getting our hands dirty with RIP configuration using the same topology that we've used for the last few videos. At this point, there's no static routing configured. To start with, we simply enter router RIP to start the RIP process. On a Cisco router, all routing protocols run as separate processes, which only runs if we use this router command. This is also where most of our RIP configuration goes. For example, we can now enter the command version 2. Remember that we can use RIP version 1 and RIP version 2. RIP v1 should never be used anymore, so this command forces us to use RIP v2 only. Our next step is to use the network statement. This is sometimes misunderstood, so I suggest paying attention to this one. The network statement enables RIP to send messages on any interface with an IP that's covered by this range. You might notice there's no subnet mask used with this command. Even though RIP v2 supports classless networks, this command is still classful. So when we entered network 172.16.0.0 on R1, we told RIP that it is allowed to send update messages on the 4 gigabit interfaces, as they all have IP addresses in the 172.16.0.0/16 network. These messages are sent regularly and contain a list of networks that this router knows about. RIP v1 broadcasts these messages to all hosts on the network. RIP v2 is a little more elegant and sends them to multicast address 224.0.0.9. Sending these update messages to a multicast address means that only routers listening for RIP messages will get them. This is much more efficient than a broadcast. RIP messages will not be sent further than a single hop. So, for example, if R1 starts sending updates to R2, R2 will not forward these messages to R3. It may create and send its own update messages, but it won't forward the exact message it received from R1. We also need to use a network statement for 10.0.0.0, but there aren't any routers connected to the 10.0.0.0 networks, so why would we want to do that? In addition to enabling interfaces to send updates, the network statement will also tell the router that it's allowed to advertise the connected networks in that range. And here's the bit that sometimes confuses people. I know it confused me at first. The purpose of this command is not to advertise 10.0.0.0. The purpose is to advertise any connected network within 10.0.0.0. Of course, for this to be useful, we need to enable RIP on another router. Over on R2, we're putting in the exact same configuration. Part of enabling RIP is not just sending out update messages, but also being able to receive and process them. We can see this in action with the show IP protocols command. This command gives us information on all routing protocols configured on the router. It just so happens that RIP is the only one we have configured right now. In the RIP section, we can see the routes that we've added with the network command. We can also see routing information sources, which is a list of the routers that are sending RIP updates to us. When a router sends these updates to other routers, it will use the IP of the egress interface as the source IP. If you're not familiar with the term egress, it refers to traffic leaving the router. So if a router sends a RIP update out the GI01 interface, it will use the GI01 IP as the source address. This probably sounds obvious, so why am I talking about it? Because of the way the receiving router handles this message. The update message contains a list of several networks, and all these networks go into the RIP database. Ultimately, some of these may end up in the routing table. When this happens, the router will use the IP address listed as the source IP in the update message as the next hop. Now that the router has learned about some networks, it can share them with its neighbors using its interface as the source IP. In this way, all routers through the network can learn the routes. If we go back to our lab topology and look in the routing table, we can see that we have now learned some RIP routes on R2 and that R1's IP is the next hop. You'll also notice a timer next to the route. This is how long it's been since the router has heard an update on this route. And of course, we can filter the routing table for RIP routes only if we want to, just like we did with static routes a few videos ago. It's now time to share something really interesting. RIP v2 isn't classful like RIP v1 was. However, it still has some classful roots. We saw an example of this with the network statement earlier, no subnet mask. Another thing that RIP v2 will do by default is to summarize to a classful network. Look at R1. It has 3/24 networks in the 10.1 range. RIP will not advertise each of these networks. Instead, it will automatically summarize these into the classful 10.0.0.0/8 network, and it will advertise that instead. It's essentially saying, if you want to reach anything in the 10 range, send traffic to me. But can you see where this might be a problem? Look at R4. It also has networks in the 10.0.0.0 range. So it will also advertise the exact same summary route. Poor old R5 is going to get the same route, 10.0.0.0/8, advertised from both R1 and R4. It then has to choose between the two of these so one can go in the routing table. LPM and administrative distance are the same in both cases, so they won't help. The end result is that R5 won't have all the information it needs to make a good decision. The solution then is to disable auto summary on each RIP router. This tells RIP not to do any summarization unless we tell it to, causing it to send the real /24 routes. I recommend always disabling auto summarization. Summarization itself is not a bad thing. In fact, although it's a bit too advanced to get into right now, summarization is really useful. But we want to control this ourselves. We don't want the router automatically doing this for us. We should now do the same on R1, of course. And if we look at the routing table, we can see the correct routes. I've quickly added all the RIP config that we've just seen to the rest of the network so we can focus on the next big thing. Remember the network statement we used earlier? It enables RIP messages on our router's interfaces, and it advertises connected routes. What would you do though if you were faced with a situation where you had to advertise a connected network, but you don't want to enable RIP messages on a particular interface? For example, take a look at R5. It's connected to an ISP router, which is managed by a third party. We generally wouldn't want RIP sending our routing information to a third party, but we still want to advertise the 172.16.200.0 to the rest of our network. To solve this problem, we can configure an interface as a passive interface. We'll do this for GI0/1, which connects R1 to R5. RIP messages are no longer sent out of GI01, but its connected network is still advertised. Show IP protocols shows us that this interface is indeed excluded from RIP. Let's put that back in for now and look at an alternative approach. I prefer this method myself, which is to set all interfaces as passive by default. We then disable this on any interface that we do want to participate in RIP. I find this to be a bit more secure, as we can't accidentally have RIP turned on. Notice here that the loopback interfaces are now missing from this list. Seeing as we've mentioned security, another option available to us is authentication. We can require each of our routers to include an authentication string in their update messages. Routers that receive these messages will check if the string is correct before accepting these updates. This is done to protect against rogue routers. Imagine a silly scenario where someone in your office bought in a router from home and connected it to the network. They could use this to influence how routing works, which is completely unacceptable to us. If we configure authentication, we can prevent this from happening. So let's configure the link between R1 and R2 to use authentication. We start by defining a keychain. This is a list of passwords that we can use. On a Cisco router, keychains can be used for all sorts of things, not just RIP. Inside the keychain, we create a key. The key is our password. If we wanted, we could create several keys and have our routers cycle through them periodically, but that's a bit advanced for now, so we'll just stick to one. Unlike most other RIP configuration, we apply this directly to an interface. This is because we could use different keychains for each interface if we wanted to, or perhaps enable it on some interfaces but not on others. First, we need to set the type of encryption. This can be set to plaintext or MD5. We don't want to use plaintext, as this would send the password without encrypting it first, meaning a hacker or someone malicious could read the password with very little effort. MD5, on the other hand, encrypts the password before it sends it. And second, we choose the keychain that we want to use. Of course, we then need to go to R2 and configure the settings there as well. If we don't have the config matching between the two routers, they won't be able to share routes. If we show IP protocols now, we can see the keychain listed. This is handy for troubleshooting. Let's take some time to consider something that's critical to routing protocols: the metric. A metric is simply a way to measure something. Metrics for time include seconds, minutes, hours. Metrics for weight includes kilograms and pounds. A distance vector routing protocol uses a metric to measure the distance from the local router to the destination network. RIP uses hop count as its metric. For example, from R1, the network 10610 is 2 hops away using this path. It is also 3 hops away using this path, and 3 hops away using this third path. R1 will learn about the 10610 network from R5, R3, and R2. It won't build a map of every link beyond these routers. It just uses these as signposts. This is how distance vector routing protocols are different from link state. What it will do is it will look at the hop count, and it will find that one path is shorter than the rest. In RIP's mind, the shortest path is always the best path. So it takes this information and it puts it in the RIP database. We can take a look inside the database with show IP RIP database if we want to. See our path to 10610 with the number 2 next to it? 2 is the hop count. You might notice that some networks have more than one entry in here. This happens if there is more than one path with the exact same metric. Routes from the RIP database are offered to the routing table. If these have the best administrative distance, the router will put these routes into the routing table. Looking at the routing table now, we can see the route to 10610, and next to it is the administrative distance, 120, and the metric, 2 hops. All routing protocols make use of a metric of some sort. OSPF, for example, gives each link a cost, which is based on how fast the link is. Slower links have a higher cost, which are less preferable. EIGRP uses several bits of information to make a metric, including bandwidth, latency, load, and reliability. Often EIGRP metrics are very large numbers. The important thing to remember is that each routing protocol will select the best paths it knows. It will offer these to the router to use in the routing table, and the router will select the best route using administrative distance. Take some time to talk about 2 key characteristics of distance vector routing protocols. These are split horizon and route poisoning. When we configure routes, we need to be careful not to create loops in the network. If you've been trying out labs in the last few videos, you will have seen where this can go wrong. Dynamic routing protocols are no exception. They also need to prevent loops occurring in the network. One of the ways they do this is with the split horizon rule. Imagine that a router receives information about a route from a neighboring router. This will say, use R1 to get to this network. One of the things this router will need to do is share this update with its other neighbors. How does it do this? The simple way is to send a message out each interface saying, use R2 to get to this network. Unfortunately, this comes with a problem. R1 is telling R2 how to get to the network. At the same time, R2 is now telling R1 how to get to the network. A packet flowing through here may be forwarded to R1, which then gets forwarded back to R2, and then gets stuck in an infinite loop. So to solve this, the split horizon rule simply says, when a routing update is received, send it out all interfaces except the one it was received on. So in this case, R2 will send an update to R3 and R4, but it will not send it back to R1. Simple and elegant, isn't it? Another elegant solution is how bad routes are handled. Imagine that R1 is connected to a network that goes down for some reason. R1 will now want to advertise that this network is gone, so other routers can remove this path from their routing tables. To do this, it sends a network update that marks this route as unreachable. The way this is done depends on the routing protocol. RIP has a hop count as a metric. The maximum hop count RIP will allow is 15. So if R1 wants to tell the entire network that a particular network has been lost, it can set the metric to 16. This is an invalid hop count, so other routers that receive this update will see this path as invalid for this network. To put it another way, this route is marked as unusable. This will be left in the routing table for a short time, and then it will be removed. And this brings us to a concept called convergence. Let's consider what would happen if R3 failed, perhaps due to an unexpected power outage. R1 and R3 are directly connected together. When R3 fails, the link between R3 and R1 goes down, causing R1's interface to go down as well. R1 can immediately see that there's a problem and can start working on finding alternate paths through the network. Recalculating paths when there are changes in the network is called convergence. What about the routers that are not directly connected? Take a look at the path between R3 and R5. They may be one hop away, but they're not directly connected. There is a switch in between. So, if R3 were to fail, the link from R3 to the switch will go down too. However, the link from R5 to the switch will not go down. R5 will not immediately know that R3 is down, so it needs some other way to discover this and to converge. To handle this, RIP uses 4 different timers. The first is the update timer. This is how frequently route update messages are sent. The next is the invalid timer. This timer tracks how long it's been since a route has been updated. Each individual route has its own timer. Every time a route update message comes in, this timer resets to 0, so in a healthy network, this timer will be reset every 30 seconds. If this timer counts up to 180 seconds without receiving an update, then something is clearly wrong, and this would be the case if R3 failed. The router will mark this route as invalid. This is also called the hold down state. When a route enters the hold down state, the hold down timer starts. During this time, no updates for this route will be accepted. This stabilizes the routing table while it's converging. That is, it gives the router enough time to find another valid path before flooding it with new information. And the final timer is the flush timer. This begins at the same time as the invalid timer, but it counts up a lot higher. It also resets when new updates come in as well. By default, this is 60 seconds longer than the invalid timer. This means that for this 60-second overlap, the router will advertise that the route is invalid to its neighbors. This is when it's using the metric of 16. When this timer finally expires, an invalid route will be removed from the routing table. These timers, at least in their default values, are very high. Because of this, it can take several minutes for a network to fully converge when there's a problem. This is one way that RIP is significantly inferior to other routing protocols. So how do we manage the default route? We can't simply throw in a network statement for 0000 and expect it to work. Why is this? Because it doesn't match any connected route. We can't advertise a route that we don't own. We could configure a static route on all routers, but that's a lot of effort, and it won't respond to changes in the network. What we can do is pick the router closest to the internet and configure a static default route there. Then we can use RIP to advertise this default route to the rest of the network. This is simply done with the default information originate command. We could use this command without the static route, but that would cause a problem. Once the traffic reaches R5, R5 will need to know what to do with it. So it still needs a default route in its routing table. And to verify this, we can log on to R2 and see that it's learning the default route through RIP. In fact, it happens to be learning 2 usable paths. ACLs are a versatile tool, which can be used for many different purposes. But while they have many uses, their most obvious function is as a packet filter. That is, to allow or deny traffic. Packet filters add security to the network. Perhaps we want to limit the workstations that are allowed to log onto routers, or maybe we want to allow only HTTPS traffic to a server. We can use ACLs in both cases, to allow some traffic, but to deny others. An ACL is really a collection or list of rules. Each of these rules is called an access control entry, or ACE, and is used to permit or deny traffic. Each entry in the list is evaluated in order from the top of the list to the bottom. Every entry contains some match criteria. This may include information like source address, destination address, protocols such as TCP and UDP, and port numbers. When a packet comes into a router, the router will look at this information in the packet header. It will compare this against each entry in order to see if it matches any of the rules. If the router finds that the packet matches one of these entries, it will then look at the action. The simplest actions are permit and deny. As you would expect, if the action is permit, the traffic is allowed through. If the action is deny, the router will block the traffic. It's important to understand that each rule is evaluated in order. See how there's a number next to each entry? That's the sequence number. This number determines the order the rules are evaluated in. As soon as an incoming packet matches one of these entries, the action is applied. At this time, the router stops evaluating more rules. The key point from this is that the first match wins. So when you create ACLs, it's important to consider the order of the rules, otherwise you may not get the results you want. But what happens if none of our entries match incoming traffic? There's an invisible rule at the end of the list called the implicit deny. When the entries we've configured don't match, the implicit deny entry will drop the traffic. Is this a good thing? Yes, it is. We can't think of every rule to cover every possible scenario. Aside from making our jobs too hard, it would make our ACLs far too complicated. So, for security, if we're not expecting the traffic, the router will drop it. If you're really observant, you may have seen that some of these masks look backward. No, it's not a mistake. And this is not a subnet mask, although it does look similar. This is a wildcard mask. The subnet mask that you're used to uses binary ones and zeros to show which part of an IP address is the network and which part is the host. You can check out the How IP Addressing Works video if you'd like a refresher on this. A wildcard mask, on the other hand, is used to match addresses. The zeros refer to the parts of the address that need to match the address in our rule. The ones are the parts that don't need to match. So in the example above, the wildcard mask says that we're looking for any IP address that starts with a 192.168.10. We're also saying that we don't care what the fourth octet of the IP address is. So the address 192.168.10.12 will match our rule. However, 192.168.22.1 will not match. This probably raises a question in your mind. Why do we bother using wildcard masks at all? Couldn't we just use a subnet mask? Well, a wildcard mask does have an obscure advantage. A subnet mask requires all the ones and the zeros to be grouped together. A wildcard mask, though, does not have any such restriction. This means that we can perform some advanced matching by mixing up the bits which are turned on or off. In the example here, the 192.168 part must match, as those bits in the mask are set to 0. Also, the .1 at the end needs to match as well. But the third octet can be anything at all, as this is where the wildcard bits are. So 192.168.10.1 will match, but 192.168.10.2 will not. Why would we ever want to do this? Granted, there are rare cases, but think of a case where we have several subnets, and the router in each one uses the .1 address. An ACL like this could be used to allow management traffic to the router, but deny it to everything else. If you can think of a few examples like this, please share them in the comments below. This type of ACL is called an extended ACL. This is only one type of ACL. There are also several others. Each of these have a different functionality, but as this video is an introduction to ACLs, we're going to ignore most of them for now. We've seen the extended ACL already. The other main one is the standard ACL. This is the first one that Cisco created and is much simpler. The standard ACL can only match based on source address. That's it. It can't look at the destination, the protocol, or the ports used. I prefer extended ACLs myself, but you will see standard ACLs out there. One way we can configure ACLs is to give them a number. We configure each entry individually, and any entries sharing the same number are part of the same ACL. This number also determines if this is a standard or extended ACL, as you can see in this table. If you're looking at doing an exam, I would try to remember these ranges if you can. It wouldn't surprise me if you got a question that related to this. Aside from picking a number in the right range, no particular number is any better than any other number. They just simply act as labels to organize the entries into a list. The more modern alternative to numbered ACLs is named ACLs. In my opinion, these are much better. Every list has a name and acts like a container. Entries are nested inside the container. In addition, there's no ranges or numbers to worry about. During configuration, we simply tell the router if this is a standard or extended ACL. This will probably make more sense when we try it in a lab a bit later on. We now have a pretty good idea about how ACLs are built and what they can do. But on its own, an ACL does nothing. Nothing at all. Right now, the router doesn't know how to use the ACL. After all, it doesn't know that we want to use it as a packet filter. So we need to apply the ACL to one or more of the router's interfaces. When we apply an ACL to an interface, we also have to apply it in a direction. There are two directions, called ingress and egress. Ingress means when traffic is coming into the router. Egress is when traffic is leaving the router. So when we apply an ACL, we apply it to an interface with a direction. Take note though, there can only be one ACL per interface per direction. Let's run through an example. When traffic enters this interface, that's the ingress direction, the ACL will be evaluated. If the ACL allows the traffic, it will continue through the router and eventually need to exit from interface GI0/2. That's the egress direction. We have no ACL applied here, so the traffic will automatically be allowed. Now what happens if the traffic flows the other way? There's no ACL applied to GI02 in the ingress direction, so the packet is allowed. The packet will need to leave from the GI01 interface. There's no ACL there in the egress direction, so the packet will be allowed to leave. You can probably see that it is important to understand the path that the packet takes when you're creating your ACLs. There are two VLANs, 10 and 20, which contain workstations and servers. Each VLAN uses a different subnet. There is a router, configured as router on a stick, to pass traffic between the two subnets. Right now, all traffic is allowed between the subnets, but we want to restrict this a bit. So we're going to attempt two goals. Goal 1 is to block regular HTTP traffic to the servers, but allow HTTPS traffic. Any other traffic to the servers should be denied. Goal 2 is to allow the server, but not the workstations, to manage the router with SSH. Nothing should be allowed to manage the router with Telnet. No other IP traffic to the router should be prevented. The starting configuration has already been done, so we won't need to worry about that. As usual, the topology is downloadable from the website, and I'll put a link in the description. Starting at goal number 1, we're going to create a rule to block HTTP traffic to the servers. If we use the access list command, we can configure a numbered ACL. Here you can see the different ranges we can use. For now, only worry about standard and extended. If we were to configure access list 1, we get the options for a standard ACL. If we try to deny HTTP traffic here, you will see that we don't get many options to choose from. Remember that standard ACLs only match on the source IP address. Instead, let's try to configure an ACL from the extended range. See how we now have many more options? Don't worry too much about all of these. Just focus on IP, TCP, and UDP. We can use IP to allow or deny any traffic between certain IP addresses. TCP and UDP can be used to block or allow specific ports between certain IP addresses. In our case, we want to block HTTP, which uses the TCP protocol. The next step is to configure the source address, that is, where traffic is coming from. We want to block all HTTP traffic. If we wanted to, we could get more specific and only block traffic if it comes from a particular source port, but that's not important for our goal. So we'll move on to the destination IP address. So what destination should we use? Should we create a separate rule for each of our servers? Well, if you look at the topology, you can see that we don't have to, as all our servers are in their own subnet. Can you see now how it's useful to separate our resources by VLAN and subnet? Now we need the dreaded wildcard mask. Don't worry, it's an easy one. We only need to match the 192.168.20 part of our address. We don't care about the rest, so our mask will be 000255. We're at the last part now, which is the matching port number. There's a few options we could use here. The most common option is EQ, which means equals. We use this when we want to match one specific port. Some other alternatives include range, for matching a range of ports, as well as GT and LT, to match ports greater than or less than a particular number. We're going to keep it simple and match one single port. We could write in 80 as HTTP traffic uses TCP port 80, or we can make use of some of the well-known values that iOS has made available to us. At the very bottom of this list, you can see that www is used for HTTP traffic. It really doesn't matter if you use this list or if you just type the number in, they both work. And our first entry is done. We can check this with show access lists. Remember to use the do keyword if you want to run this command from within configuration mode. We now have one access list, number 150, with a single entry. This is good, but our ACL is not done. We now need an entry to allow HTTPS. So we now repeat the process, this time permitting HTTPS, which uses TCP port 443. And while we're at it, we can add a remark to the ACL. A remark is just a comment that makes it easier for us to understand what we've configured later. Looking at the ACLs now, we can see that there are two entries. The new entry has been added to the bottom of the list. The final part of our goal is to block all other traffic to the servers. How do we handle this? It's actually simpler than you may think. Although it's not shown as an entry in our list, there is that implicit deny rule at the end. Any traffic that we haven't matched will automatically be blocked. In fact, we don't really even need a rule to block HTTP, although it can be handy, as you'll see soon. So are we done? Almost. We still need to apply the ACL to an interface, in this case GI0/1.10. For this, we need to enter interface configuration mode and enter the IP access group command. We give it the ACL number and then we give it a direction. This is the ingress and egress directions we were talking about earlier. If we want to verify this, we can use show IP interface and look for the outgoing and inbound access list entries. And it's difficult to test the results of this in a lab, but we'll give it a try. Over on the workstation, we can use the Linux command curl to try to retrieve a web page from the server. It immediately fails when using HTTP. If we try again on HTTPS, it still fails but with a different message. This message means that traffic is reaching the server, but the server doesn't have a web page to give back. So the ACL is actually allowing HTTPS traffic, but because this is in a lab, it's hard to show that. And how about ping? This no longer works as the traffic isn't getting past the packet filter. That's because of the implicit deny rule at the end of the ACL. I didn't originally intend to block ping, but I've done this accidentally. This should show that when working with ACLs, it's easy to overlook things like this. So it's really important that you test your changes thoroughly. Let's take another look at the ACL on the router. Do you see how each rule now has one match? This is from the traffic that we just generated. This is another way to see that our lists are working. You'll notice though that there's no match counter for the implicit deny rule. This is one reason why sometimes it's useful to create deny rules like we did for HTTP, even though we don't seem to need them. While we're looking at these rules, do you see how each rule starts with a number? In this case, it's 10 and 20. These are the entry's sequence numbers. This shows the order the rules are evaluated in. We can give rules sequence numbers if we want, but if we don't, iOS will automatically assign numbers like it has done here. Now to move on to goal number 2, where we only allow SSH from the servers and not the workstations. If we try SSH on the workstation, you can see that part of our job is already done. The ACL we've already configured is already denying SSH to the router. That's the implicit rule once again. This will also be blocking ping and telnet. To block telnet and allow SSH from the servers, we need to create a new ACL, which we will apply to interface gi0/1.20 later. For some variety, we'll configure this one as a named ACL. Named ACLs are configured with IP access list, and there's no need to worry about number ranges here. We can just use the extended keyword. And now we'll give it a name. We'll call this one Server ACL. This brings us to the named ACL subconfiguration mode. The NACL in the prompt means named ACL. This is quite different to when we configured the numbered ACL. Similar to before, we want to deny telnet traffic from any source. However, the destination IP address is just a single IP, the IP of the router. So to simplify things, we can use the host keyword as the destination and enter our single IP address. This means we don't need to worry about a wildcard mask. The rest of the command is just like the one we saw earlier, but before we issue the command, I would like to show you the optional log keyword that we can put at the end. This is used during troubleshooting. When we add this keyword, the router will create a log entry each time the rule is matched. I don't recommend turning this on unless you need it, as it decreases the router's performance. So I'm going to leave it turned off for this entry. Now we can put in a rule to allow SSH to the routers from the servers. You might think we're done, but there's one more thing to think about. Our goal said that we need to allow any other IP traffic to the router. Right now, the implicit deny rule is blocking all other traffic. So we need to add a rule to allow all other traffic. This is a very simple rule that permits IP traffic from anywhere to anywhere. And finally, we just need to apply this to an interface like we did before. Have we finished now? So close. Our original ACL is also blocking all other traffic to the router. We can easily put in a rule at the end of the list to permit all other traffic, but only to the router's IP. From this, you can see that we can add more rules to an ACL at any time we want. I recommend that you try all of this in a lab yourself, whether with a downloadable lab that I provide or with one that you build on your own. Office networks often have many devices, and with that comes many IP addresses. We don't want to manually configure every single device with its own IP address though. We also don't want to reconfigure every phone, tablet and laptop as they roam through the building. The solution then is to automate the process of handing out IP addresses. This is what a DHCP server can do for us, so we're going to see how it works and how it's configured. Think of a computer that's turning on for the first time. It won't have an IP address. A DHCP server can help with this, but our new computer doesn't know where to find it. So it creates a special DHCP discover message. It then broadcasts this message out to the network. This message contains the computer's MAC address. Regular devices will see the packet and ignore it. DHCP servers, on the other hand, will be very interested. The DHCP server contains a database or pool of IP addresses that are valid for the local network. So when it receives the discover message, it knows that the new computer needs help. It looks in the address pool, it finds an available IP, and it temporarily reserves it. It will then put this information in a DHCP offer message and send it back to the client. Sometimes this is sent as a broadcast, and sometimes as a unicast message. The reason why is a bit too complicated to go into now, but if you're interested in finding the answer yourself, have a look at RFC 2131. What happens in a case like the one we're showing here, where there is more than one DHCP server? Well, the client will get more than one offer. So in our example, a client has received 2 offers. It will select one and formally ask permission to use it by broadcasting a DHCP request message. The server finishes up the process by sending a DHCP acknowledgement message to the client. This is where the server officially allocates the IP address. The client is now free to use the IP and any other information that the server may have given it. We'll cover the extra information soon. Requesting an IP from a DHCP server is a 4-message process. If you want an interesting way to remember this process, just think of Dora the Explorer. We've been talking about a dynamic allocation of IP addresses. We also have the option of a static allocation. This is also called a reservation. This is where the DHCP server is configured to give a specific IP address to a specific client. The client is identified by its MAC address. So when the discover message comes in, the server sees the client's MAC address, knows that it's meant to give this particular client a special IP, and puts that IP into the offer message. There are a few cases where you might want to use this, but they're not too common. See if you can think of a few cases where you might want to use this feature and put them in the comments. When a DHCP server sends the offer message, it will also send a lease time. This is the time for which the IP address is valid. Windows servers, for example, will offer a lease of 8 days by default. Cisco DHCP servers, on the other hand, have a default of only 1 day. Of course, we can set these values to whatever we need them to be. By the way, if you're interested in digging deeper into the DHCP message format, I'll put a link in the description that you can have a look at. If the lease were to expire, the DHCP server will put the IP address back into the available pool. The alternative is that the client may want to renew the lease. It will attempt to do this halfway through the lease period. So with a Windows server, for example, the client will try to renew after 4 days. The server will try to be nice to the client. It will try to let it keep the IP it already has. However, there is no guarantee, so the client may end up with a completely different address. A client may choose to send a release message to the DHCP server saying that it's finished with using this IP. This is not a requirement though, so it's completely okay if the client doesn't give the IP back when it's done. If you're working with Windows, here's an issue to be ready for. Sometimes a Windows machine will have an IP address like this one, starting with 169.254. This is called an APIPA address and usually happens when this machine could not get an address from the DHCP server. To force Windows to try again, we can run ipconfig/renew. Often we use the release and renew commands together. This is useful, for example, if we have updated our DHCP server with some new information and we want the client to get a fresh IP. But DHCP servers aren't just good for handing out IP addresses. They can also hand out extra pieces of information called options. There are many different options that can be configured, but there are a few common ones we should discuss. The router option gives the client the IP address of the default gateway. The DNS server option tells the client about DNS servers on the network. We're going to talk about DNS servers in the next video. The domain name option tells the client which domain it's a part of. This is quite important in Windows environments. And finally, the TFTP server option gives the client the IP address of a local TFTP server. We won't get too deep into TFTP, but this is a server that transfers small files. For example, we can back up our switch and our router config files to a TFTP server. This is critical though when you have phones on the network. When the phone starts up, it gets an IP address and TFTP server addresses through DHCP, and that's where it downloads its config files from. We've seen that the DHCP process starts with a client broadcasting a discover message. Can you see the problem that we could face here? Broadcast messages are only useful on the local LAN segment. This is because routers do not forward broadcast messages. When a client broadcasts the discover message, it will not reach the DHCP server. So when we have several LAN segments in our network, how can we provide DHCP services to them all? Well, one option is that we can put a DHCP server in every LAN segment. Or maybe we could give our DHCP server a network card that connects to each LAN segment. And we might do this in some parts of our network, but that adds up as a lot for us to manage. The simple alternative is called a DHCP relay. We can configure an interface on a router to act on the DHCP server's behalf. When a client broadcasts a discover message, the message reaches the router that is configured as a DHCP relay. The router is configured with the IP address of the remote DHCP server, so the relay will then send the message directly to that server. The server responds to the message by sending the offer to the router. The router then forwards this on to the client. This is a very efficient method, as we can have a server with all the DHCP configuration in one single place. You will regularly find DHCP servers running on Windows, so I'd like to give you a brief look at how it's configured here. Here we have the DHCP console, just after the DHCP role has been installed. We're going to create a new IPv4 scope. The scope is just the Windows name for the DHCP pool. Naturally, Windows has a wizard for this, and we start by giving our scope a name. Next, we configure the first and last addresses in the pool, as well as a subnet mask. Usually we don't want to hand out all addresses in the range, so now we can configure exclusions. These are the IPs that we don't want handed out dynamically. And now we can configure the lease time. By default, this is 8 days on Windows, but just for fun, we'll set this to 4 days. We can now configure extra options that we can hand out to the clients, so we might as well do that now. First, we configure the default gateway. This is the router option. Now, the domain name and DNS servers. There's a DNS server in here by default, but we can add more if we want. Our DHCP server will try to contact the DNS server to confirm it's up. It's not available from our lab environment, but it still lets us add it if we want. As this is a Windows server, we can add Wins servers if we want to. This is a relic of the old days, and for most part we can completely ignore this now. And finally, we can choose to activate the scope now or later. So why not now? Inside the scope, we can see the address pool. And in here we can see any leases. This is any IPs which have been handed out to our clients. Our server hasn't handed any out yet. We can also create a reservation if we want. This, as we discussed earlier, is if we want to reserve a particular IP for a particular device. For this, we need a name, an IP address, and a MAC address. And it doesn't look like Windows likes the format that I'm using, so hang on a sec, let's try a different format. It doesn't like that either. It looks like it just wants letters and numbers, which I guess that's fine, I suppose. And finally, we can see the scope options that we configured earlier. Now, let's try and make this more interesting, and we'll try to configure this on a few Cisco routers. Here we have a small topology with 2 networks, 2 routers, and 2 workstations. R1 is going to be our DHCP server, and it will need to hand out an IP address to workstation 1. Workstation 2 will also need an address, but it's on a different subnet, so we're going to have to configure R2 as a DHCP relay. So let's start by configuring R1. The first thing to do is to define a pool with IP DHCP pool, and then give it a name. This is exactly the same as the scope we saw earlier on the Windows server. The next part is to configure the network. This is the network address and subnet mask that makes up the addresses in the pool. We can't configure a specific start and end address like we did in Windows. The default router is the IP address of our default gateway, so we'll choose 172.16.10.2. And next, the lease. We'll choose 4 days in our example. The domain name is quite self-explanatory, as is the DNS server. The next server is a bit more interesting, and its function may not be immediately obvious. This is used to configure a TFTP server, which we talked about earlier. So this is the part we need if we want to give phones their configuration files automatically. And that's it for the pool itself. But there is still something else we need to do, and that is to tell the router which IPs should not be given out, using the IP DHCP excluded address command. We need to take care not to allocate an IP address for anything that's static, like our router's IP address. If we don't think about this, we face a potential IP conflict. So if you have servers and printers with static IPs, make sure you exclude these IPs from the pool. Now we should test it out on workstation 1. Usually a workstation like this would request an IP address while it's booting. In this case though, the workstation already booted before DHCP was configured. So we'll use the dhclient Linux command to request an IP address. The -v gives us more information so we can see the entire process. Interestingly, the request and offer are displayed in a different order here, but we can still see that we're being given an IP address, and we can see the server that gave it to us. Now, are you ready for something really interesting? Back on the router, we have a console message which says that there has been an IP conflict. The router tried to give out 172.16.10.2, but this is already in use by R2. Fortunately, the router was able to detect this and give out a different IP address instead. It's great that R1 discovered this automatically, but we could be in trouble if, for example, R2 had an ACL that blocked lots of different traffic types. If R1 cannot detect that there's a conflict, we would definitely be in trouble. So, we're best off adding this IP address to the excluded address range. We need to configure a pool on R1, and we need to configure the DHCP relay on R2. We'll stick with a very simple pool in this case. This shows that most of the configuration we used earlier is optional. Now to configure the relay. On a Cisco router, we use the IP helper address command, and we use this on the interface that will be receiving the discover messages. If we try the same command on workstation 2, we can see that this is also successful. Notice that the offer seems to be coming from R2 and not R1. That's because it is making the offer on R1's behalf. There are 3 verification commands which are very useful, especially if you have troubles getting DHCP working. Firstly is the show IP DHCP pool. This shows pool statistics, including pool size and how many IPs have been allocated. It is possible to run out of IPs, so keep an eye on how many IPs are left. Next, we have show IP DHCP binding. This shows a list of each IP address that has been allocated. Let me just make this window a touch bigger so it all fits in a little better. And here we can see the IP address that has been allocated, the MAC address it lines up to, and the date that the lease will expire. And finally, we have Show IP DHCP Server Statistics. This one is very useful for detailed troubleshooting. We can even see the message types and how many have been sent and received. We've all typed an address or a domain name into a web browser and loaded a web page. But we know that computers use IP addresses to communicate, so how does a web address turn into an IP address? This is achieved using the Domain Name System, or DNS. Much like your phone, which can find a phone number to match a contact, a DNS server can find an IP address to match a name. The internet without DNS is truly unimaginable, so let's take some time to appreciate how this indispensable service works. Before we look at how DNS works, we need to understand the domain name space. Here we have a typical name chosen completely at random. As you can see here, there are several parts to this name which are separated by dots. Here we have www, network direction, and net. Even though we don't always see it, there's always a dot at the end too. Often web browsers and other applications hide it, so we don't often think about it. This full name is called the Fully Qualified Domain Name, or FQDN. Now this may not be obvious to look at, but a name like this one is part of a hierarchy. It's a bit like creating a family tree. We read a name like this from right to left, starting with the dot. The dot is the root domain and represents the start of the family tree. Under that comes the top-level domains, or TLDs. In our case, this is net, but there are other types like com and org and others. Sometimes there's even a country included, like co.uk or net.au. Under the TLD comes the second-level domain. For us, this is network direction, but this could be almost any name. In some cases, we would find more subdomains under that. In our case though, we have a host name, www. For our example, this host name is used to represent our web server. Now we can think about how a DNS server fits into the picture. The DNS server contains one or more special databases called zones. The zones represent the domains, such as networkdirection.net. Each zone contains pieces of information called records. There are different types of records, which we'll look at soon, but the most common one is the host record, also known as the A record. And this contains the name to IP mapping for all the hosts within this domain. Windows Server is probably the easiest way to get started with DNS, so we're going to have a look there. Over on the left, we have forward lookup zones and reverse lookup zones. For now, we're interested in forward lookup zones. And here we have a zone that I created earlier. I would like to take this opportunity to encourage you to build a small lab and try creating your own zone. And don't worry, it's not very hard to do. Inside our zone, we have a few records. The top two, the start of authority and the name server records, are special records which are used to describe the details of the zone and the DNS server. The next two are both A records, which hold a name and its IP address. In both cases, they're pointing to my server. There's not a lot to them really, they're really quite simple. If a DNS server has a zone for a particular domain name, then this server is authoritative for that domain. So this server here is authoritative for networkdirection.net. This means that the server believes that it knows all there is to know about this domain. So if someone tries to look up mail.networkdirection.net, this server will simply say, no, this record does not exist. Why is this important? Well, because if this DNS server is non-authoritative for a domain, it's willing to admit that it doesn't have all the answers and it may ask another server for help. And we'll see that happening in a few minutes' time. If you want to see some of this in action, you can run the nslookup command from a Windows command prompt. Linux has a similar command called dig. We can try two lookups. Notice that one is non-authoritative. This means our DNS server doesn't own that domain. There are a few more record types that you will probably come across. We'll take a quick look at 3 of them now. Over here we've got the reverse lookup zone, and with that belongs the pointer record. This is the reverse of what we've discussed so far, as this is used when you know an IP address but you don't know the name. And the zone itself looks a bit different. As this relates to IP addresses, each zone is named after a subnet. Also, the FQDN is in reverse, which I guess is appropriate for a reverse lookup zone. And it's always followed by the text in ADDR ARPA. This is a fixed string of text that indicates that this is a pointer record. Okay, so the next one of interest is called a CNAME or canonical name record. This, really simply, is just an alias. For example, we already have an A record called www, but we might also want a new record called web, and it should point to the same IP. So one of our options is to create a CNAME record which maps web to www. And this is really good if the IP address changes. That means we only need to update one of our records, not all of them. And the last one we'll look at quickly is called a mail exchanger or MX record. This is how we advertise the IP addresses of our mail servers out to the internet. So say a mail server somewhere out on the internet wants to send us some mail, it will look up this record, it will learn the IPs of our mail servers, and it will know where to send the mail to. Now we'll take a moment to look at a simple DNS lookup process. Here we have a DNS server and a client. The client is configured with the IP address of the DNS server. This can be done manually, as we're showing here, or the client can be given the IP of the DNS server through DHCP. When the client needs to perform a name lookup, it sends a message to the DNS server using UDP port 53 as the destination. This message includes the fully qualified domain name that it's looking for. When the message arrives at the server will check if it is authoritative for this domain. In this example it is. So it will look for the requested record inside the zone. If the record is there, it will then return the IP address to the client. On the other hand, if the server does not have the requested record, it will send a message to the client saying that it does not exist. And as this server is authoritative for the requested domain, it can indeed say this with confidence. When the client gets this result, whatever it may be, it will store it in the local cache. It does this for performance, so it won't need to ask the server again for some time. But how long is it stored in the cache? That's based on a value called the TTL, or time to live. If we enable advanced view here, and then we open a record, we can see the record's TTL. And this is set to 1 hour. So this record would stick in the client's cache for 1 hour and then it would be removed. Once it's gone from the cache, if the client needs the record again, it will need to perform another lookup. If we open a command prompt on Windows, we can look at the cache. First we'll ping an address by name to perform a DNS lookup. And now if we type in ipconfig/display DNS, we can see the record in the cache. New records get added every time there's a lookup. What happens though if a change is made to the A record on the server? Our client won't know about the change until the record has been cleared from the cache. So for troubleshooting, you'll occasionally want to clear out the cache manually. On Windows, you can do this with ipconfig/flushdns. I've got a few quick troubleshooting tips for you now. If DNS is not working, start by checking the DNS settings on the client. You can do this in Windows with the ipconfig/all command. If there's no problems there, try pinging the DNS server to see if it's even responding. If the server's down, it certainly can't help. Then try clearing the cache, which we went through just a few moments ago. And if none of this is working, you can always try bypassing the DNS server entirely and setting manual records. On Windows, we have something called the hosts file, which contains manual entries. You can Google that yourself if you'd like to have a look. And on a Cisco router, we use the IP host command to enter manual entries. Keep in mind though that bypassing a DNS server should really only be done for testing. You don't want to leave those records in there permanently, as it can confuse your results in future. Now let's get to a more complicated example. Think about when we need to look up a name on the internet. Let's imagine that our client wants to browse to this URL. First, it will need to perform a DNS lookup to resolve blog.cloudflare.com to an IP address. So just like before, it sends a message to the DNS server. However, our DNS server is non-authoritative for the cloudflare.com domain. So how does it handle this query? Our server simply can't answer this query on its own. So now it becomes the client and sends a query to another DNS server. If the outside DNS server knows the answer to this query, it will send the answer back to our server. Our DNS server will cache the result to save time if it's asked again, and will send the result to the original client. The server's cache follows the same rules, and the cached record will be removed when the TTL expires. This process, where the DNS server finds the answer on behalf of the original client, is called a recursive query. Here's an interesting thought though. How does our server know where to send this query? Surely there's thousands of DNS servers out there on the internet. One option is to configure the DNS server with a forwarder. This is one or more IP addresses that our server can send requests to. The other option, if no forwarders are configured, is to use root hints. Remember from earlier that the dot at the end of the FQDN is the root of the namespace? Well, there are 13 IP addresses for special DNS servers around the world, which are called root servers. These are authoritative for the root namespace, which means that they know how to find the name servers for top-level domains like .com, .net, .org, and so on. So going back to our example, the client sends a request to the DNS server, which the DNS server doesn't know how to answer. The server has no forwarders configured, so it relies on the root hints process. DNS servers come pre-configured with the 13 IP addresses for the root servers, so our server will pick one, and it will send it a query asking where blog.cloudflare.com is. Now the root server doesn't have all the answers either, but it does know how to find the DNS servers that are responsible for all .com domains. So the root server will send back a message called a referral containing the IPs for these servers. This type of request is called an iterative query. This is different to a recursive query, as our server is just getting hints back. The root server doesn't take over the process, our server still has to work it out on its own. And so the process repeats. Our server sends a request to one of the .com DNS servers that I just learned about. This server also doesn't have the full answer, but it does know which DNS server to use for cloudflare.com, and so it will send a hint for that back. Our server continues the process and sends a request to the Cloudflare DNS server, and finally we've found the server that is authoritative, and it returns the answer that we're looking for. And just as before, the record is put in the DNS server's cache, and a response is finally sent back to the original client. For the most part, we use private IP addresses in our networks, but the internet uses public addresses. So how do we make these two work together? We need a device to translate between these two types of addresses, and for that, we have Network Address Translation, or NAT. Let's see how this works and how it's configured. Think of the header on a packet. This contains the source IP address that the packet was sent from, as well as the destination IP address that the packet is being sent to. NAT is the technology that can take an IP address in a packet's header and replace it with a different IP address. The most common use for NAT, as mentioned at the beginning of this video, is to translate between public and private IP addresses. This is part of a strategy to save public IP addresses across the globe. Decades ago, the intention was that every device would have a public IP address. However, there's a limited number of public IP addresses available, and we started using them far too quickly. So these days, we mostly all use the same private ranges in our networks. But to connect to the internet, we need public addressing. So a router between our network and the internet will translate private IPs to public IPs and back again. And if you're wondering, we will generally have public IP addresses given to us by our internet provider, and they often won't give us very many. How does this work? It's all based on the IP header. Every packet has this header which contains a source address and a destination address. A router has a set of rules about which traffic should be translated and which traffic should be left alone. When a packet arrives at a router, the router will examine the IPs in the header to find traffic that matches a NAT rule. If a packet matches a rule, then this router will rewrite the source or destination IP address in the header and send the packet on its way. We can even configure NAT to change port numbers in a TCP or UDP header if we want to, but we'll save that one for later. There are two types of NAT. These are source NAT and destination NAT. Source NAT is the most commonly used type of NAT. As the name suggests, source NAT changes the packet's source IP address. This is generally used for internet access, as we explained earlier, where we are using private IP addresses in our network. The router takes the private IP in the header and replaces it with a public IP. Devices on the internet see this packet as coming from a public IP, and they are able to send traffic back. The router will change the IP address back to a private one as the packet passes through. The alternative is destination NAT, which is a bit less common. As you've already guessed, this is where the router changes the destination IP address rather than the source IP. We might use this if two organizations have merged and they were already using the same IP space. Normally this wouldn't work as they need to have unique IPs. However, we could use NAT so each network thinks that the other is unique. This scenario is a bit complicated, so we'll leave this one alone. Some devices can translate both the source and the destination IPs. This is typically the role of a firewall which has advanced NAT features. We do have a video on configuring NAT on the ASA firewall if you'd like to see that in action. It's a bit more complicated though, but it's worth a look if you're interested. But in this video, we're only going to look at source NAT for internet access. Before we get right into the configuration, there's a couple of terms to understand. When we configure the router, we specify which interfaces are inside our network and which are outside. Cisco uses the terms local and global to describe the inside and outside. Keep in mind that different vendors will use different terms for this. When a device first creates a packet, it puts its own IP address in the header as the source. This IP address is called the inside local address. This is the real IP of the host inside your network, and it is probably a private IP. The outside IP is the destination address. This is the IP of a device outside of our network. Technically, this may not be the destination's real host IP, as NAT may change it, but this is what our hosts think is the real IP. After a packet has a NAT rule applied, different terms are used. The source IP address is called the inside global address. This is our host's IP address after it has been translated. For internet access, this is now likely a public IP. The outside global IP is still the destination address. This would only change if we configured destination NAT, which is not the case in this example. Configuring static NAT, also known as one-to-one NAT or basic NAT. A static NAT will take a local IP address and statically map it to a global IP address. These two IPs are always a pair, and the mapping does not change. We would typically use this if we had a server on our network, maybe a web server, that we want to make available over the internet. People on the internet can then access our web content using the public IP that we configure in the static NAT. The downside to static NAT is that we use up public IP addresses very quickly, as we need a public IP for every static NAT rule. Bidirectional NAT. When we think of NAT, we often need to think about where the traffic is initiated, that is, where traffic starts. For example, traffic may start on a workstation with a web server on the internet as the destination. The web server will then send traffic back to the workstation. This means that NAT is applied in a particular direction, and that direction depends on where the traffic starts. Consider the example we just configured. There is a web server inside our network, and people outside our network need to reach it. The server can initiate a connection to the internet if it needs to, or something on the internet can initiate a connection to the server. The NAT we configured will work, no matter which direction the traffic is going. This is a bidirectional NAT. The opposite of this is called unidirectional NAT, which we'll see at the end of the video. But for now, let's consider how to configure NAT for our workstations. Usually we won't use a static NAT for this, as we have a lot of workstations and not many public IPs. One option we could consider is dynamic NAT. This does not use a one-to-one mapping between a private IP and a public IP. Instead, we can create a pool of public IP addresses and let the router map an IP to each workstation as they're needed. Closely working hand in hand with NAT is port address translation, or PAT. In fact, they're so closely related, we usually just use the term NAT as an umbrella for both of these technologies. If you remember back to when we looked at TCP and UDP, you will remember that they also use headers. And in these headers are source and destination ports. Just as NAT rewrites IP addresses in the IP header, PAT rewrites port numbers in a TCP or UDP header. In most cases, PAT and NAT will work together, so one will be changing the IP address and one will be changing the port number. This is quite common when we want to make a few services available to the internet by port number alone, rather than translating the entire IP address, which exposes all of a server's ports to the internet. We need to discuss which some may consider the most important of them all. This one is called port overloading, or masquerading, or many-to-one NAT. Think of a case where we don't have many public IP addresses available to us. Maybe we've only been given one or two by our service provider. In a case like this, we can't use a dynamic NAT pool like we did earlier. This is because dynamic NAT will map one public IP to each host that needs internet access. We'll very quickly exhaust the pool of IPs, and any additional traffic will be dropped. So it's clear we need an alternative. This is where port overloading comes in. This is still a form of dynamic NAT and PAT, but the router will translate ports as well as IPs. In addition to the pool of IPs, the router has a pool of ports that belong to each IP address. There are about 64,000 ports in each pool. Now think of the first workstation accessing the internet. It sends a packet to the router, which contains the source and destination IP and port numbers. The router will rewrite the source IP with the public IP address, and it will also rewrite the source port with a port from the pool. The router keeps track of which ports have been used and which workstation is using them. This way it knows where to send return traffic. Now when the workstation wants to access the internet, it goes through the same process as before. In our example, it gets the exact same public IP as the first workstation, but it will get a different source port from the pool. In this way, devices on our network can share a single public IP address as they each use unique source ports for each connection they open. And as there are about 64,000 TCP ports and 64,000 UDP ports, we won't run out of ports quickly. NAT, where traffic can be initiated from either the inside or outside of our network. Port overloading behaves differently. This is an example of unidirectional NAT, where traffic must be initiated from inside of the network. Return traffic is fine, of course, but the connection needs to start on the inside. Why is this? Because the router builds its table of port to IP mappings dynamically as connections are needed. So if someone tries to connect to a workstation from the internet on a particular port, it's highly likely that that port is not already in the translation table.
Imagine you have around 100 routers and switches across your network, and all the links that go with them. Everything's running well, and you're thinking about having the day off. But then, everything starts to slow down. People are complaining that phone call quality is poor, and they can't access the internet. And guess what? It's up to you to figure out which of your 100 routers, switches, or links is the problem. What tools will you use to solve this? Of course, you have logs on your syslog server, but wouldn't it be great if you had a server that monitors the health of your network? You could find your problem, or maybe you could even see the warning signs before you even have a problem. And that's what SNMP, or Simple Network Management Protocol, is all about.
It's a protocol that enables you to monitor and manage the health of the network. A management server will use SNMP to collect information about devices on your network. This can include details like link speed, CPU and memory usage, temperature, fan speed, and many more. One simple way it does this is through a process called polling. At regular intervals, which could be every few minutes or every few seconds, the management server will send out an SNMP message using UDP port 161 to the devices that it manages. This message asks each device questions about its current health, and the devices respond with their answers. Polling is very proactive, as you can see the status of your devices at any time. The other way this can work is with SNMP traps. This method does not rely on the server to frequently send messages out to the network. Instead, when devices have something worth reporting, perhaps a fan has stopped spinning or the CPU is getting too hot, it will send an SNMP trap message to the management server. Traps are very reactive, as they wait for an event to happen before notifying the server. We don't have to choose between polling and traps though, we will generally use a mixture of both. Now that the server has this information, there's usually a few things it will do. It will record the information for historical use. For example, we might want to see what our peak time periods for internet usage are. It will provide information to us in the form of graphs, charts, and so on. This might include the percentage of uptime across our network, for example. It can provide a web-based dashboard with the overall health of the network. Sometimes this might look like traffic lights, where green means healthy, orange or yellow is a warning that something's not right, and red indicates a definite problem. And it will also send us alerts when problems occur, or maybe even if it's predicting a problem. For example, we might get an email saying that a file server has less than 10% disk space left. This is a case where we can fix an issue before it becomes a real problem.